the senior scientists, and also the panelists like Professor Ravinanjaya, Swadhin Behra, Ashok, Oxy, Subodh.
Dr. Surya, we are not able to hear you.
Cannot hear me. Okay, can you hear me now? Maybe I have to
Yes,
talk.
yes.
It's much better.
Okay,
It's much better.
good. Okay, good morning to all of you. And this initiative on ICTM, International Council for Tropical Meteorology, is one initiative that has been initiated at IATM, and we are looking forward to a successful implementation of the ICTM with all your cooperation and suggestions. So this association will try to maybe work with other tropical meteorology groups and also monsoon groups across WMO. And I invite all of you to actively participate in this workshop and panel discussion. And with that, I will hand over to Sila.
Thank you, sir. Thank you, sir. Thank you, sir, for your words. Now, may I request Dr. Gyanishilan, Project Director at IATM and the coordinator of today's workshop, to kindly deliver the welcome address.
Good morning, everyone. Special thanks to Dr. Annalisa for coming online in the very early morning hours. And first of all, I welcome all of you, both the participants at IATM and the speakers and panelists coming online. So, Director Dr. Surya Rao, Dr. Tara, ICTM lead member, and my dear friends. Today we are going to organize a one-day workshop, a panel discussion on monsoon variability, predictability, and prediction. So this is the third activity in a series of activities we planned under ICTM. And this is going to be one of the full day program. The previous two events were mostly confined to panel discussions. And so we are going to address one of the challenging areas in meteorology, understanding monsoon variability, predictability, and prediction. So hope we will have very active sessions and a lot of discussions during the presentations and panel discussions. And we have experts from different parts of the world. Hope this will be a very eventful workshop panel discussion. Thank you.
Thank you, sir. Thank you for your warm welcome address. May I now invite Dr. Thara Prabhakaran, Project Director at IATM and a lead member of ICTM, to kindly brief us on the objectives and activities of ICTM.
Thank you all. It's a real pride and privilege for me to present to you regarding the ICTM today. First of all, I am really very much thankful to Director IATM and Dr. Gyanishilan for organizing this event. Actually, my role with ICTM is energize each member to organize activities which may be beneficial for students and early career as well as other scientists. So actually ICTM is a commission. I also want to recognize all the online members here. Thank you so much for contributing to all these talks and discussions that we are going to have today. And ICTM is a commission that is under development, I would say, under the International Association of Meteorology and Atmospheric Sciences. So this is what is about the international. Actually, the ICTM comes under IAMAS, which is the International Association of Meteorology and Atmospheric Sciences, which is under International Union of Geodesy and Geophysics. That is the IUGG. IUGG has several associations, almost 8 associations, and meteorology and atmospheric science is one association among that. So actually, IAMAS promotes major focus or research areas in atmospheric sciences, and also it leads an alliance for capacity transfer with WMO as well as UCAR. So also there are this is all done by voluntary scientists. Okay, voluntary efforts of scientists. And the idea is to bring out the science, and there are many commissions under the IAMAS. So currently the IAMAS is chaired by Professor Andrea Flossman, and she is the president, and Keith Alberson is the Secretary General, and there are a few officers in there. And I'm just quickly going to the ICTM. Actually, ICTM is currently we are thinking of making it official in the upcoming meeting in the IAMAS assembly in Busan. Hello. So there are nearly 25 experts selected from all around the world. Currently we have 20 experts, but we can go up to 25 experts in the field. And the idea for ICTM is to organize several meetings or conferences centered around this tropical meteorology fields. So what do we do with ICTM? It is to enhance research in tropical meteorology by organizing thematic conferences, workshops, symposias, and enhance understanding of tropical circulation systems using observations and models, and also exchange scientific ideas and international collaborations in tropical meteorology, facilitate support for students and scientists to attend relevant conferences organized by the Commission, and also establish working groups and committees, joint committees for under the ICTM. Also, all these the events or meetings, joint efforts that will be reported to IUGG through IAMAS. Okay, now going to. But we have indeed, there were a lot of discussions, online communications, and there were few topics. These are all the topics that are selected under the, or considered under the ICTM. And you can also see that under IAMAS, there is one website for ICTM where all these topics are listed. And these are the contributing members. And the timeline was actually, it all started in March 24. So now we are at a stage where we are we are discussing on specific themes of panel discussions and the planning for the ICTM. And all of these preparations, all the activities will be reported in the upcoming Busan assembly, and you will see that listed in the events under the Busan assembly. And thereafter we will have further meetings considering all these panel discussions. Recommendations of the panel discussions will be considered under the ICTM to formulate its vision, further vision and mission. Okay, so finally, I'm not taking too much time, but these are the events we have conducted, or including today's event. And there are also some more planned events, events in the list. Some are date we have to determine, and also there will be one early career scientist panel, which we will be discussing later. Thank you.
Thank you, ma'am, for your kind words and for highlighting the purpose of ICTM and today's workshop. We now commence the technical sessions of the day, begin with the keynote talks. May I now humbly request Dr. Surya Rao, Director of IATM, to kindly deliver his talk on challenges in modeling monsoon simulations and prediction. Sir, over to you. Dr. Surya Rao, sir, is the Director of the Indian Institute of Tropical Meteorology. He led the prestigious Monsoon Mission program of the History of Earth Sciences. His expertise spans in coupled climate modeling, Indian monsoon prediction, and climate variability.
Morning, everyone, and thanks to the organizers for giving me an opportunity to talk about the challenges in simulating and predicting monsoons. So I'll directly go to the challenges, and also I try to give you some opportunities that are available. So first and foremost challenge that one has to look at in simulating the monsoon is that the challenge number one is Indian monsoon is too active if you are only looking at the standalone AGCMs, and also too weak in coupled general question marks. This is the first challenge. So if you really want to predict or simulate monsoon, these are the challenges that one has to look at it. So for example, in 2014, there was a WCRP grant challenging to identify the grand challenges in the WCRP. One workshop has happened in 2014, and they have shown that this is the observed. So if you look at this is the observed rainfall distribution or India having clear centers of convection located at three different locations, one at the equatorial Indian Ocean, another one is at Eastern Bay of Bengal, and another one at West India. So these are the three centers that are supposed to be simulated very well by the models. But if you look at coupled model, you see that it is highly underestimated. This almost more than 10 to 20% underestimation of rainfall in the center at the head bay of Bengal. So others are slightly overestimated, but that is not too much of. So if you look at uncoupled, then the whole of India rainfall is overestimated, as I mentioned here. Indian monsoon is too active in uncoupled simulations. So if you are increasing the resolution, also this problem at head bay of Bengal still stays there. So over the years, if you look at the CMIP 3, CMIP 5, CMIP 6 models, you can see them here. The problem of coupled models underestimation of rainfall is very much there in almost all versions of the all generations of the coupled models. And if you look at the biases also, they are almost similar. So not much of change between CMIP 3 to CMIP 6. So this is the biggest challenge, that getting monsoon in models is one of the biggest challenge. That is what we have to look at. There are several studies have been done by people. So I will show you an opportunity also. So what people have noticed is that in the coupled models, mostly the synaptic variability is very much underestimated. So if you can get synaptic variability correctly, for example, here low pressure systems of form over Bay of Bengal and Arabian Sea are plotted here. You can see that the tracks of the low pressure systems go all across the Indian subcontinent. So if you look at MMCFS, that is a earlier version of the model, they don't penetrate deep into the Indian landmass. So in MMCFS2, they start penetrating into Indian landmass. So what the people, the group Moran et al. 2025 identified that if you have freshwater plus the models, also very high resolution in the coastal regions, then you will be able to get all these monsoon freshwater floods, monsoon winds, and cross behaviors correctly in the model. So therefore, it will improve the circulation and it leads to larger temperature gradients in the Bay of Bengal. That is coastal difference will be generated. Then that will accelerate winds and creation of lows will happen, and that will again create eddies. So by having a very high resolution models and also freshwater floods, you can ensure that some of these low resistance propagate deep into the Indian subcontinent. So in the if you look at the AGCM standalone models itself, then what you see is that this is the SST convection or SST OLR relationship. This is 90 percentile, this is the mean, this is 1 sigma. So what you see that in the observations after reaching 28, the convection almost rainfall is about 12 millimeters per day. It is what you get most of the 90% of 90 percentile time. So if you look at the GFDL model, or again, these are all the again coupled models. It goes sometimes in the uncoupled, it goes beyond uh, up to 20 millimeters. So what is happening in the AGSM is that if you see warm SSTs, it is trying to convert immediately, and also it is almost linear relation. So the SSTs as SST increases, the rainfall also increases, and it reaches up to 20. So that is why in AGCMs you have a problem of representation between SST and convection, and you also always get more than what is expected rainfall over the landmass. So that is same problem is there for almost all other models. So, if you are really want to get your monsoon correctly, the models. So these are the some of the opportunities, but there are several others also will be there. I'm just giving you an example, which has proven very clearly that by doing this, you can get monsoon simulations little better than previous one. So the challenge number two, if you look at it, it is the low pressure scale. This is a slide from during IATM Diamond Jubilee lecture by Professor Shukla. What he had shown is that the enormous correlation coefficient of 3.4 is almost 0.7 in the last several decades. So this is the mean scale that is there about 0.7. If you look at the same thing for monsoon, it is about 0.2, the mean scale for monsoon and fall. So there is a big gap between what is achieved in the SST indices of 3.4 in the first week and what you can achieve for a monsoon rainfall is 0.2. So this is a large difference is there between SST prediction and rainfall prediction. So this is how people have started thinking that why this skill is very low for monsoon. That is one of the challenges. And but fortunately, there are a lot of good work has happened at IITM and other places. So that has really improved these skills. So the reason is one of the reasons is that low variability. That is very signal is internal variability is less than about 10% or close to 10% is the maximum internal variability that can reach it if you take all India averages. But if you look at individually, it is about 20 or less than 20 millimeters per day is the internal variable that is there. So 20% this is. So if you look at again SSTs, sorry, you cannot see this. It is more than 40 to 50% internal variability is there in this region. So the signal is very strong in tropical first week. When it comes to rainfall, it is less than 10 or around 50 if you are looking at different locations. So this is one of the other challenges that you have to have strong signal to get better predictions. But if you have very weak signals, then how do you get your predictions or simulation correctly is by looking at very high resolution and resolving the different scales of phenomena. So that is the way, that is the opportunities that you have to have very high resolution models, and also you have to resolve the scale interactions from synoptic to extended range or intraseasonal oscillations to seasonal mean, then to RF. So those scale interactions are very much required to be captured correctly. then only you'll be able to get this low variability also correct in the model. So another challenge that you have is that this is the paper by Prashant Pillai in 2022. What he shows, this is the, you look at for time being only the black curve. So what it shows that in recent times, the Monsoon relation is almost close to 0.8. So it's very strong relation is there between ENSO and ISMR. So in spite of the strong relation, you have to initialize your models from the spring predictability barrier window. So if you look at these statistical models and empirical models, which can explain the ENSO variability, what we see that in February, if you initialize February models, you will get about 5% of the internal variability of 3.4. So in March, you may get up to 20 to 30, and in April, about 40. But you look at other months like September, October, they reach up to 80% of the internal variability can be captured easily if you initialize your model in these months. Unfortunately, when you make monsoon forecast, you have to look at only this window, that is spring variability barrier for predicting and so phenomena in the tropical spring. So if you look at these are the again and so prediction scale over time with the different. So we are interested in JJA. So you can see that the scale, if you look at this period, and particularly the spring, is very low. So compared to here, there is here the scale is very low. Whenever you try to predict JJ SSTs or JJ rainfall, the scale is very low, particularly when you are trying to initiate the model using February, March, April initial conditions. So this is another challenge. So you have to get rid of this challenge to have your models having very good scale by in June, July, August SSTs. Then because they are very tightly coupled, like ENSO and Monsoon are very tightly coupled in the observations. So you have to get SSTs in the tropical speed correctly. Then only you can get better prediction skill or simulations again in the models. So the other big challenge is the ENSO-SMR relation. If you look at these are the indices, 1.2, 3, 3.4, 4. So if you look at all these indices, if you are, these are the observations, they are very weak. If you look at each month wise. If you start with them each month, then the skills are, the relation is, the correlation between ENSO and IS is very low. But whereas if you look at models, they are very high. So they are almost double or sometimes it is more stronger. So this is another challenge. So sometimes the ENSO ISMR is overestimated and the ISMR IOD is underestimated. So the teleconnections, which are very important for predicting and simulating the monsoon in the our Indian region, is actually depends on these two infrared more sensor and IoT. But however, if you look at your models, they are very much, there are different models are there. You can see that this is FMCFS, but if the same thing is problem for any other model. Okay, so this is another biggest challenge that you have to fix to get better simulation and better predictions in the models. So the challenge 6 is the impact of underrepresented components on monsoon variability prediction. So there are so many components that still we don't represent properly. So this is a very nice paper by Decadal in 2021. What this is that if there is a dirty environment like more dust and aerosols in the monsoon gets strengthened. That is what they say, that if you have more dirty environment, the monsoon is good. But there are a lot of uncertainties in concluding this. So if you are clean air and less aerosols and less dust, then this is not going to be a very good signal for monsoon. So, but it looks like going for more dust and more aerosols is good for monsoon. That is counter to think that this is what will create. But they also say that this is just one scenario, but there could be another components. If you get those components right in the models, this may not be correct as well. So as far as they concern, this is the mechanism that dust leads to heating, and it also not just amount increase, and it increases the low level jet and moisture transport. So therefore the monsoon rainfall over Indian region improves. So similarly, if you look at ocean biogeochemistry, that also has a lot of impact on simulating monsoons by modulating the SSTs and mixed layer depths in the region. So they actually create a lot of feedbacks. So these are the feedbacks that we still have to get them in the models correctly. Then your monsoon simulations and other predictions may improve further. So I'm not talking about the predictability part in this lecture, but the prediction of this. So I'll try to give you some examples on how different model developments by incorporating different components have increased the prediction scale in different scales. So for example, if you are having freshwater floods, so if you try to represent freshwater floods in the model by calculating on a river routing model, so you can get wave stability correctly. So therefore, you can have better skills for both Ivory Coast, Lana, and all these things. Also, SAC also improves for different regions. This is also very important. So if you try to improve the data scale by using the core reflex algorithm, then also you will get a lot of improvements in slow relations and also the intraseasonal SSTs by integration of intraseasonal cycle. So all these things can be get improved further. Most importantly, the diagonal amplitude is very, very weakly represented in the models that can be improved further. So as we all know that all these prediction problems, whether prediction problems, prediction value problems. So if you start using coupled data simulation, then you are going to reduce the good mean square error in the analysis. Therefore, it also reduce the before correct errors. So that will not is established already. So resolution, as I said, it always improves, but by simply increasing the resolution doesn't make any difference without understanding the physics behind it. So you have to change your parameter skills also with resolution, then only you can get better results from improving the model resolution. So there is a converted parameter scheme reverses. It has shown a lot of improvement in both in ENSO and ISMR scale, 0.5 to 0.65, 0.4 to 0.57. So like the microphysics, and also if you add more and more components, then also you get better skills. So now the skill model skill is about 0.72, which was earlier 0.5. So not only that, even the ENSO skill has moved from 0.65 to 0.84. So therefore, because the ENSO skill is improving, so you get similar improvement in the monsoon also, as I mentioned as a channel number 3 also. So once you get the spring variability within the spring variability barrier also, better skill for monsoon SSTs in the Indian tropical first week, then that will definitely reflect as ISMR scale. So I'll give you examples of this. This is an improved microdisc process. This is as a control 15 paper. So what is showing? This is the control PDF of the OLR. You can see that it is completely away from the observations. So we have more OLR bins are more beyond 240 and all 220, but in the peak is at about 210 is the what permit square is the OLR is the peak. So whereas in the model is very different. So once you try to represent different microphysical process in the model correctly, then you can see that beautifully the whole PDF is actually captured very well in the model. So this is one example of you are working with cloud microphysics. People normally think that by changing just microphysics, how do you get much of a response? Because each and every component is connected to each and every other component. So these things really matters a lot. So by representing the freshwater fluxes, you can see that this is the Taylor plot. So you have river is where the freshwater flux is represented, and the other one is the control. You can see that compared to the control, the ISMR scale improves significantly, and not only improved, now also it is close. Coming variations also much better represented in the model. So similarly, for in the 3.4 also it is improved. It was overestimated in the control run that is now coming close to observations. So same thing happens to ICMA scale also. So if you look at this is a spatial pattern, so you can see very clearly that our Indian region compared to the control run, you get more reds. That means the skills are improved.
Please summarize.
Yeah. So the same thing that if you improve the diagonal variability in the models, then also you see that the sensitivity experiment that you see here, they are very well shows much improvement compared to the original control runs. So there is a promise here that if you improve any of these components that I mentioned before in the table form, so you get a lot of improvements. By improving the monsoon simulations or predictions, then you also get similar improvements in the Nino 3.4 or other Atlantic regions also. So that is the logic is very simple. Once you don't get this large scale heating pattern or associate the monsoon correctly in the models, then you will not get other things also correctly. So it is improving monsoon simulations and monsoon prediction is pivotal in improving the other modes of internal variability. So if you miss that, then your skills will for others modes also very low. So by doing all these things, you can see that compared to other next generation models from GFDL and ACMM, when you come out this, our model skills are much better by improving all of them. So it has not only resulted in improving the monsoon skill, but also in other modes of the variability. So this is what is the message. Okay, so that I'll start. So we are now taking up a very ambitious project that is crystal clean up Earth, wherein we are trying to improve incorporate all these AML models to make the predictors much more useful and also impactful. So I will not, since there's not much time, I'm not going to details, but this is what is the future that we are looking at. So that I will go. So the other opportunity is that when we started working on these monsoon simulations and all, we had only 2.3 teraflops HPC. Now we have about 11.7 teraflops. It is almost more than 1600 times improvement in the computational resources. So this is not only at IITM, it happens similarly at other places. That's how you'll be able to improve your monsoon simulation applications. Thank you. I'll take any questions.
Thank you, sir. Thank you for your insightful words. So we will move on to the next. May I now kindly invite Professor Ravi Nanchutia to deliver his talk on understanding the intraseasonal variability in extreme monsoon years. Sir.
Yeah. Would you like, you will be presenting it and or should I share my presentation?
You please try to share from your side. If it doesn't work, we will share.
Yeah.
Professor Ravi Nanchutia is a professor at Center for Atmospheric and Oceanic Sciences, the Indian Institute of Science, Bangalore. His expertise lies in monsoon studies using climate and mesoscale models and the application of high-performance computing in climate and weather research.
Can you give me share permission, please?
Yes, sir. Yeah. Sir, over to you, sir.
Okay, thank you. So, good morning to all of you, and I thank Dr. Sheelan, Dr. Tara, and of course everybody at IITM, including the director, Dr. Surya, for giving me this opportunity to talk about this particular subject, which is about active break cycles, the relationship with intraseasonal oscillations, and finally how they kind of impact the intraannual variability. This is a, can you just go back, please? Yeah. So this is a work of my student, Ritesh. It's a work under ongoing work along with my colleague, Dr. Ashwin Sheshadri. Please go to the next slide. So all of you are familiar with active and break cycles. We all know that rainfall in a season is not always continuous. Sometimes you have long periods of high rainfall or low rainfall, usually which we describe as about ±1 of standard deviation. And if the periods of high rainfall, we call them as active spells, and the periods of low rainfall we call as break spells. Sometimes long spells of high rainfall could lead to low rainfall, could lead to below normal rainfall. For example, here we have 2 years. The one at the top on the left side is the 1975, when there were very few breaks and there were more periods where there was active rainfall happening. And 2002, which was a drought year, when you had long periods of breaks. So in a sense, you could see that if there are very long breaks, they tend to be kind of lead to below normal or a drought-like year or a drought-like situation. So what we can say is that active break cycles, which is an intraseasonal feature, can lead to modulation of intra-annual variability. Please go to the next slide, please. So if you look at active and break spells, so here what we are looking at is not just for all the years where we are looking at active and break spells. We are looking at in extreme years, that is the flood years and the drought years. And we kind of took the criteria of flood and drought years based on the criteria of 10%, which is the all-India summer monsoon. And based on it, the drought years were these, and the flood years, which is larger by 10%, were these following years. And if you look at the break spells in drought years, you had 27 of them. And you had active spells in all the drought years, being 16 of them. That means you can see a huge asymmetry, that there are a larger number of break spells in drought years and a smaller number of active spells in drought years. Similarly, if you look at flood years, you see 6 break spells of the 5 years that we have analyzed, and 23 active spells. Again, you can see kind of an asymmetry with larger number of active spells in flood years as compared to drought years. So basically, we can say that if you have larger or longer droughts, for more frequent break spells and longer break spells, they could lead to kind of a drought monsoon or a below normal monsoon. Please go to the next slide, please. So we analyze these active and break spell in extreme years. So if you look at the active spells, they are more frequent in flood years, that is about an average of 4.6 than in drought years, which is an average of about 2.3 per year. And duration, of course, of these active spells is similar. That is, in both cases, you find them to be of 3 to 4 days. And so here we have the breaks on. If you look at on the right side, you see the figure. The first figure at the top shows the break spell is in flood years and their frequency and their length. So if you look at break spells, they tend to be of 3 to 4 days, and of course one as long as 9 days, which was an extremely long break spell. If you look at break spells in drought years, you have a frequency which is kind of a maxima at around 6 days, and or could be as long as about 12 days. Of course, you can see that the break spells in flood years and also are asymmetric in the sense that you have fewer number of break spells, plus also longer duration break spells tend to be higher during drought years. If you look at active spells during flood years, they tend to be usually of the order of about 3 days, which is the maximum. Of course, you can have something as long as 7 days. But it's interesting to note that if you're looking at break and active spells, there's an asymmetry that you don't get the same kind of long active spells, even in flood years, as compared to the break spells, which could be as long as 12 days, or one of them which we saw was about as long as 14 days. And if you look at the active spells in drought years, they tend to be very short duration ones, which is typically of about 3 to 4 days, and only one of them we could see as about 7 days. So in a summary, we can say that if you're looking at break spells, the frequency they are more frequent in drought years, which is about 3.9, as compared to flood years, which are about 1.2 per year. And they are longer in drought years, which could be 6 to 7 days, sometimes greater than 10 days, versus flood years, where they could be about 3 to 4 days. Next slide, please. So that was one aspect of intraseasonal oscillation, that is these active and break spells. Another way of looking at it is its movement, space-time movement, and what we call as the intraseasonal oscillation over the Indian region. I mean, there are been umpteen number of studies from everywhere around the world, and especially from IITM and also from some of the Indian institutions. So if you look at the intraseasonal oscillation, it has a very rich intraseasonal structure. It was first noted by Sika and Gadgil in 1980, and at the same time, almost at the same time, by Yasunari in 1879. It consists of poleward moving cloud bands. If you look at the left side, there are two figures. Well, the top one is for 2005 and the bottom one is for 2011. And you can see that there are poleward moving cloud bands with typical periodicities which occur about 20 to 60 days. And it's interesting that it's ubiquitous features of the Indian region. That is, it occurs almost every year. You can see them. And the other region where also it is common year after year is West Pacific. You may see northward or poleward propagations in other parts of the world, but it is kind of most ubiquitous over the Indian and the West Pacific regions. And in some years, you may have very significant propagations, as you can see in 2005, these arrows as they show. They could be less frequent, but you can still kind of, by the eye, you can see that there are still the poleward moving cloud bands, which also occurred in 2011. So if you're looking about the structure, the genesis occurs over the warm waters of the equatorial Indian Ocean. And that is around, let's say, around the equator or slightly south of the equator. And they move northward and culminate over the monsoon trough region, which is around about, let's say, 20 to 25. Next slide, please. So now what we want to look at is the ISO and the break spells, how these ISO are related to the active and break spell, and how they are kind of, what is the nature of how ISOs kind of modulate the active and break spells. So that's the study that we are trying to do. And this actually, there was a previous work which was also done by Krishnamurthy and Shukla, followed by a work by my student, Nirupam Karmakar, along with Arindam. So we have used MSSA to understand the structure of ISO at high and low frequency. So we try to understand the association between ISOs and active and break spells. And first, then we discuss how active break spells vary in strong and weak monsoon years. We try to understand the association between ISOs and active break spells in strong and weak monsoons. So finally, like how they kind of modulate one or the other, like how do the ISOs kind of modulate the active and break spells. So that's the kind of more or less the theme of my talk from there onwards. Next slide, please. So we have used MSSA, which is the multi-channel singular spectral analysis, to identify the spatio-temporal patterns of rainfall over the Indian region. So for this purpose, we used IMD gridded data and also TRMM. And the period that we used for this was 1998 to 2014. And but the analysis was kind of limited to the JJS period. The details of MSSA can be seen in Karmakar et al. 2020. And when we talk of ISOs, we combine all modes between 20 to 60 days and call it as a low frequency ISO. And all modes between 10 to 20 days, we term it as the high frequency or the HF ISO. So first, we would like to see what is the structure of these ISOs, how are the LF ISOs different from the HF ISOs. And then we see when do active spells and the break spells kind of combine together, and what is the propensity of active and break spells as a combination or as a percentage, or how much variation occurs in the LF and ISO, the different phases of LF and ISO. So for that, we try to understand the structure of ISOs. Next slide, please. So first we examine the structure of LF ISO. We see a very rich structure. And for this purpose, we divide the cycle of an LF ISO into 8 phases, which could be about 4 to 5 days. In phase 1, that's the first, here you can see from 1 to 8 on the right side, the LF ISO phases. So on the first phase, you can see a negative anomaly occurs over the equatorial Indian Ocean and a positive anomaly over the peninsular Indian Ocean, peninsular India and Arabian parts of Arabian Sea and Bay of Bengal. In phase 2, there's the second figure on the right side. You can see the negative anomaly strengthens and moves eastwards. In phase 3, the negative anomalies moves over to the maritime continent, that is, which was over the south of the peninsular India, kind of now shifts eastwards and moves towards the maritime continent. On in phase 4, you see positive anomalies, which starts appearing over the equatorial Indian Ocean. Actually, if you look at it, we could kind of see, if we want to look at a proper poleward propagation, I would say that we start with phase 5 as the first one, where you see these positive anomalies occurring over the equatorial Indian Ocean, which kind of moves to eastwards. And then you can see branches happening over which moves in the towards in the northwestward direction, and another branch which goes into the southwestward direction. But as we go along further into phase 8, we find that the one on the south weakens and the one on the north kind of moves northward. And then you get these northward propagations which move to where now you come to phase 1 again, and then you see these northward, and the cycle continues. So if we look at it, then these kind of represent a typical active break cycle. So we see a northward propagation, and an eastward propagation can also be seen, as we saw from phases 5 to 8. And we also see this tilted structure, that is, it starts from, let's say, the maritime continent and goes up to Arabian Sea, which occurs on both sides of the equator. And we also notice that the variability is high over the equatorial region. So, for example, if you look at it, it kind of flips over the equatorial Indian Ocean in phase 5 to a maximum, which occurs over in the phase 7. Next slide, please. So that was the structure of low frequency ISOs, which essentially showed, if you were to look at over the Indian region, and I'm sure all of you are familiar with it, essentially a poleward propagation. But if you were to look at the structure of high frequency ISO, it is much more richer. And the phase now, of course, it's only 20 days, which we are kind of divided into 8 phases, which is of typically each of about 2 days. In phase 1, that's now if you look at the picture on the right hand side, the top one, you see in phase 1, we notice a positive anomaly over the equatorial Indian Ocean, which originates in phase 5 and moves eastwards. We see 2 tilted structures in each hemispheres, which is seen from northwest to southeast in the northern hemisphere and northeast to southwest in the southern hemisphere. And if we go to phase 2, that's the second figure, the northern hemisphere structure moves into the Arabian Sea and strengthens further. In phase 3, the northward propagation of northern band occurs, and there's a weakening of the southern band. If you look at phases 4 to 6, that is these figures on the right hand side. The last figure is the phase 4. The first figure, lower one, here is the phase 5. So if we look at phases 4 to 6, we notice a strengthening of the northward movement of the band over Bay of Bengal. That is, it kind of strengthens and moves northward, which you can see in phases 5 to 6 to 7, kind of weakens around phase 8. And we also notice 2 centers of convection, one which is over Bay of Bengal and the other over the Arabian Sea. If you look at it here, let's say if you look at figure for phase 7, you do see over the Arabian Sea also. And so if you look at the structure over Bay of Bengal, it shows a northwestward move. So the structure over Arabian Sea kind of moves northward, and before the Bay of Bengal starts moving, the Arabian Sea branch kind of starts moving up above it. We also notice a positive anomaly over Bay of Bengal and Bangladesh, which is more prominent in phases 2 and 3. It's kind of indicated by these kind of spirals, which you can see over Bay of Bengal and also parts of Bangladesh. These occur after the disappearance of the negative anomaly in phase 1. And this strengthening is put, and when we did an analysis, which I'm not going into the details of it, this strengthening could be related to the mid-latitude interactions that could be happening. And when we looked at an analysis, this is the work of Karmakar, more details are in his paper of 2020 MWR. Our analysis indicates that LFISO could be related to SST anomalies, and the HF ISO could be influenced by factors such as the upper level jet stream. So this in a nutshell is the structure of HFISO and LFISO. So if you look at it, the HFISO has a very rich structure, even though it is of a shorter duration, which includes northward movement, northwestward movement, and also an interaction with the mid-latitudes. This is a kind of a rich intraseasonal structure, which I wanted to kind of highlight, which most of us, we have looked at it in parts of it, but I thought when we do this NSASI analysis, all of it kind of comes together as part of this analysis. While if you look at the LFISO, it was essentially of a poleward movement, which kind of starts around the equatorial Indian Ocean and culminates over the trough. So that's the difference between the HFISO and the LFISO. Next slide, please. So now we look at association between active and break spells and ISO. So the figure on the left shows the probability of +1 events, that is active spells, in various phases of ISO. On the left hand, the x-axis, on the y-axis, you see the LFISO phases. And on the x-axis, you see the HFISO phases, all of them divided into the 8 phases, which we had discussed previously. And the second figure is the probability of -1, that is break events occurring in various phases of ISO. So for this purpose, we analyzed about 310 +1 events, that is active events, and 281 break events over the central Indian region. 60% of them occurred with events of +1 phases occurred in the phases of 2 and 4. That is, if you look at it, the +1 events, 60% of them moved with the phases of 2 and 4 of LFISO. And -1 events occurred in phases of 5 and 7 of the LFISO. And if you look at, in a nutshell, if you look at it, you see that the rainfall over central India is influenced more by LFISO than by the HFISO. Next slide, please. So this is a continuation of the same one. So if you look at a modulation of +1 event by the phase 5 of HFISO is less, even when LFISO is favorable. That is, if you look at the favorable condition, and if you look at the HFISO in phase 5, the probability is much lower, because this phase represents where the negative anomaly occurs over the central Indian region. Similarly, the HFISO modulated the -1 events more strongly from here. In phase 7 of LFISO, that is, if we look at it, there is a higher probability, that is the phase 7 of the figure on the right, you see a higher probability of a -1 event. That is, if you look at it here. But HFISO, which is in phase 7 here, will kind of it lowers the probability of the -1 event. When you look at the phase 7 of the LFISO and phase 7 of the HFISO, you see, and if you move along the axis of 7, then you see that when HFISO is in phase 5, there's a higher probability of -1 event. But if you move further to phase 7 of HFISO, when you see that there is a lower probability of it. So which is lower. So in nutshell, if you were to kind of analyze the association between active and break spells and ISO, we can say that LF modulates the rainfall events, while HF plays a significant role in modulating the probability of the events. As you could see in the previous example, when I talked of even if the high probability when LF ISO was in phase 7, which was unfavorable, and the probability of the occurring of an active or a break spell was modulated by the phase of the HFIs. So that's what we mean by that LF modulates the rainfall events, while HF plays a significant role in modulating the probability of the events. Next slide, please.
Can you please summarize?
Sorry?
Can you please summarize?
You want me to summarize? Sure. Okay. So how much time I have?
2 minutes.
2 minutes. Okay. So this in a nutshell shows that whenever the LFISO is in the negative phase, positive phase, you get +1 events. The same whatever I had shown, actually kind of it's shown in the form of a Venn diagram for more clarity. Then maybe you can skip all the slides, which essentially talk about the. Okay, can you just go back to the next slide, please? So if you look at the dominance of LF and ISO, so we find that low frequency ISO dominates in drought years, and compared to where it explains 36% of rainfall variance as compared to 16.7 in flood years. Similarly, if you look at the high frequency HF ISO, the dominance in flood years is about 16.7% of the rainfall variance as compared to 8.3. That means HF ISO is dominant in flood years as compared to in drought years. Over 90% of active days align with the positive phases of HF ISO, while 85 to 90% align with the break phases. In drought years, the active spells align with positive phase of LF ISO, while break days occur with its negative phase. You can kind of slip the go to the more or less the last slides, please, if you want me to summarize. Here we had looked at the structure of it and then how AI could kind of give fairly good prediction, and also recent work where NSSA was used by Bach et al. To show that for the first time you could get good predictability within the prediction capability. I would not call it predictability, but prediction capacity over the intraseasonal scale, where they kind of used a combination of data-driven models and also of the numerical models, and they could get good results. Maybe we could just quickly go to the previous slide, please. Yeah, this is a combination where they used a physical ensemble along with a meso forecast of data-driven, and it was a combination of the European forecast along with the data-driven forecast, and for they projected the physical data, the results from the physical models using MSSA along with the meso forecast, and we could see that they are able to get much more improvement in correlations as far as the lead time. That's the kind of crux of the work of the Bach et al., which was published last year. You can go to the summary slide, please. Yeah, so this is the summary slide. If there are any questions, I can take.
Sir?
Yeah.
Thank you, sir, for your talk. Let's move on to the next talk. It's our privilege to invite Dr. Swadhi Behra, Principal Researcher and Director of Application Laboratory at Jamstack, to deliver his talk on organic origins of monsoon variability in SO, IUD, and beyond. Sir, we are honored to have you with us.
Can you hear me?
Yes,
Hello?
sir. Yes, sir. We can.
Okay. Can you see my slides?
Yes, sir. Yes, sir. We can see.
Okay. Thank you. So good morning, everybody, and I especially thank Dr. Surya Rao and Dr. Gyan Silon and other organizing committee members to give me this opportunity to speak to you today. It's a pleasure. So I think in previous two talks, you already heard a lot about the monsoon. It's linked to various factors and the predictability. So we all know that monsoon is a juggernaut, and we all are trying to understand a piece of it because of our limitations and the scope of our work. We are not able to fully understand the complexity of the monsoon on its all scales and over all spaces. So that's why we try to understand a bit of it. And my role is to understand how oceanic climate variabilities like ENSO, IOD, and other ocean atmosphere interactions play a role in monsoon variability. So we all know that monsoon plays a big role in the socioeconomy of the subcontinent, not only India and its neighboring countries, but also to some extent global economy. Because monsoon is linked to various factors. A good monsoon means a good sale in gold, good sale in cars, good sale in many other things, and vice versa. So that's why the economies are linked. So we cannot say that it's only affecting our economy, but it could be affecting the global economy. And the oceanic factors that are responsible, some of them are responsible, not all of them, can be seen in this chart. We know that El Nino is a major driver. I'll come to that in a minute. And the new players are the Indian Ocean Dipole, the subtropical dipole, the Ningalu Nino, the Atlantic modes, and some other factors, even coming from the polar regions, Antarctic and Arctic. And the ENSO connection is historical. So from the beginning of monsoon research, we all know that ENSO plays a big factor. Most of the mega droughts, famine of 19th century are linked to ENSO. In fact, the southern oscillation was discovered because of the understanding of that link, how the monsoon is linked to various pressure variabilities over global region. So in that way, Gilbert Walker discovered the southern oscillation, and in that sense, the ENSO has been traditionally thought to be linked to droughts and floods in India. And we know that IOD became a new player when it was discovered. Until IOD was discovered, people thought Indian Ocean is playing a passive role in the monsoon variability. But right from the beginning of the IOD research, we try to understand the link between monsoon and the Indian Ocean. And we found that the 1994 was an unique event, which we picked up because the ENSO was not well developed that time. And India had a good monsoon rainfall that time. So that's why we thought, okay, there is something happening, because we knew that 94 was a unique case for IOD. And then later that was extended by Osaka et al. And they found that when the ENSO monsoon relationship is weakening, the monsoon IOD relationship has strengthened. And that's how they're compensating each other. The predictability comes from the oceanic waves, especially near equatorial waves, which was discovered by Rao et al. 2002 and Rao and Behera 2005. We found that the waves which propagate from Kenyan coast, the Somali coast to Kenyan coast, can give us the predictability, not only for the Indian monsoon, but for the East African rain and some other rainfalls. So in that sense, the ocean plays a key role in driving the predictability in the region. However, we know that the relationship ENSO, monsoon, IOD relationship have been changing over the decades. In the beginning of 20th century, when Gilbert Walker discovered the Southern Oscillation. That time, the relationship between Southern Oscillation Index and the Indian summer monsoon rainfall was almost one perfect correlationship. But if you see the last 10 years of the 20th century, you can see that the relationship has almost gone to zero. So, and that is the time when the Indian monsoon and the IOD relationship has strengthened. So we see that kind of a decadal shift in the ENSO monsoon and ENSO IOD relationship. And that was further corroborated by the coral records taken from Kenya, which showed that when the ENSO monsoon relationship was weakened, we see a phase shift in the IOD monsoon relationship. It was negative before. Please note that this is coral index, not SST, because SST we have less confidence for that time period because we didn't have so much of observations either in the Western Indian Ocean or in the Eastern Indian Ocean. So in that sense, coral record is a kind of proxy to give us an idea how the monsoon and the Western Indian Ocean were linked. And that showed that the IOD and the monsoon had a negative relationship before in the early part, the late 19th century and early 20th century. But there is a phase shift around the middle of the century, last century. And we see some positive phase. And then also we see in the recent years, like the late part of the 20th century and early 21st century, we see a positive relationship between IOD and monsoon. And that's what also we see when we extend the time period for monsoon, IOD, and ENSO. For the ENSO, we are taking the Southern Oscillation Index here. And for the IOD, we are taking the historically constructed SST. So we don't know how much we can give confidence to the data before 1950s, 1960s. However, in the recent period, like from 80s, when you have the satellite, we clearly see a phase shift in the monsoon and IOD relationship. It has come out from negative phase to a positive phase. And again, in the recent years, it started going back to a negative phase. So that is a non-stationary relationship between IOD and monsoon, whereas ENSO-monsoon relationship is not so non-stationary. It's basically in the positive phase for the Southern Oscillation Index. So there could be many factors. This is a research we are conducting now, so we don't have very concrete results yet. So there could be several factors in this. One is we have like intervention relationship between ENSO monsoon and also in the Atlantic Ocean. And those intervention relationship could be affecting the phase of the ENSO of the monsoon IOD relationship. And the second factor we also identified that there are coexisting other factors, other players, which were not playing a role before, but now started playing a role. We find new players which are co-occurring with IOD, and that could be affecting the phase relationship between monsoon and IOD. The third is the asymmetric relationship between negative and positive IOD with monsoon rainfall. And that could be another factor which is affecting how the monsoon IOD relationship has progressed over the decades. To tell you about the asymmetric relationship, we found that in one of the interviews in 2013, when we had a negative IOD, the business line correspondent asked us whether it will be a positive year for monsoon or a negative year. And we assumed because it's a negative IOD, we assumed that positive IOD gives to more rain and negative IOD gives to less rain. So we started thinking and saying to him, okay, we might be expecting below normal rain, but lo and behold, we had a more than above normal rainfall on the western side of the India, not so high rainfall on the eastern side of the India, either negative or negative or close to normal. So in that sense, we found a kind of different relationship between positive IOD and monsoon rainfall and the negative IOD and the monsoon rainfall. So during the positive IOD, we find that the monsoon trough regions get more rain. Central India, basically, and even the Western India, some part, gets more rain during positive IOD years. However, during the negative IOD years, we see kind of east-west asymmetry. And the western side gets more rain, eastern side gets less rain. So in both phases, India gets rain, but the regions are different. And the mechanism also is different because during positive IOD years, as we published before, the monsoon trough gets strengthened because of the rotational wind and the transport of moisture from Sumatra region. Whereas for the negative IOD years, the Western Ghat rain gets strengthened, probably the Western Ghat trough and some of the systems coming from the Arabian Sea get stronger. That's why the western side gets more rain compared to the central Indian region. There are other factors besides monsoon and besides ENSO and IOD. So we also have the Indian Ocean subtropical dipole, and there are several papers which are kind of showing how the subtropical dipole can affect the masculine high, and that in terms can influence the monsoon early circulation, and in that way it can also affect the monsoon rainfall directly. Indirectly, it can affect through triggering IOD. So there are some papers which says that Indian Ocean subtropical dipole can trigger Indian Ocean dipole, and in that way, Indian Ocean subtropical dipole can indirectly affect the monsoon rainfall through IOD. Besides IOD and subtropical Indian Ocean dipole, we have several other tropical and extratropical climate variations like the Atlantic multidecadal oscillation, the Atlantic zonal mode, the Atlantic meridional mode. They are shown to be connected to monsoon variabilities. And also the extratropical oceans like Ningaloo Nino, and the southern Indian Ocean variabilities, and even the Antarctic variabilities are linked to monsoon rainfall. I think you will hear some of them later. And we also found that the Indian landmass vegetation, terrestrial vegetation, is linked to monsoon. Many papers already said that monsoon can influence the vegetation. So that's why we have droughts when we have less rainfall because of ENSO or IOD. And then we have floods and high vegetations during La Nina and the IOD cases. So in that sense, we already understand the monsoon influence on the terrestrial vegetation, but we also recognize that terrestrial vegetation over Indian landmass, Indian subcontinent, can also influence the monsoon. As you can see in this paper by Green et al. 2017, the first one is how the rainfall is affecting the vegetation. And the second one is how vegetation is influencing the rainfall. So it's a two-way interactions. And in that sense, the vegetation also plays a role. And that's what we are trying to understand now. And this work I'm doing with IIT Kharagpur now. And then we have, going forward, all these factors can be included in both dynamical and statistical predictions. And eventually, we hope we'll have a digital twin of the monsoon so that anybody can play with it to create scenarios and also to predict the rainfall. Coming to the predictions, there are several models which are predicting monsoons now, relatively better than before. And this is a work done together with IITM colleagues, Dr. Pradhan and even Dr. Rao was involved in this intercomparison study, where we try to compare two of the best dynamical models in the world, the MMCFC and the SyntaxF of Jamstack. And we found that both models are doing reasonably well to predict the ENSO and IOD, besides ENSO Modoki variabilities. However, when it comes to the monsoon predictability, it is still not so high. It's relatively good now, above 0.5 for the IITM model and 0.45 for the SyntaxF. So, and when you do the multi-model prediction, it's slightly better. So in that sense, we are doing reasonably well, but it's not up to the level of other climate variability skills, predictability skills. So we try to also develop some statistical model. I think many of you may not be aware that before the dynamical models, we had many parameters, statistical models. So multiple parameters were used. As I showed you before, the relationships are non-stationary sometimes, and new players are coming in. So those kind of fixed parameter, even though those are multiple parameters, they are not so helpful in predicting monsoon decade after decades. So in that sense, we need some kind of sophisticated statistical model. And in that sense, the neural networks are good, and deep learning neural networks like convolutional neural network. We found some promise in predicting scale of Indian summer monsoon rainfall, especially at long lead times like 8 to 12 months. The models are doing extremely well compared to the dynamical models to predict Indian monsoon rainfall, especially by taking several variables: the sea surface temperature anomaly, the vertically average temperature anomalies, soil moisture, relative humidity, wind speed, and even the precipitable water anomalies. So, so if you take all those variables, in this sense, we are not taking any parameters. We are taking the all global variables and then trying the deep layers neural connections, and trying to identify the best models and make those best model ensembles to get the best predictions. And these are some of the heat maps to tell you.
Summarize.
Yes, I'm coming in 1 minute. Yes. So these are the heat maps, and it clearly shows you those connection ENSO, monsoon, and some other regions connections to monsoon. And as we heard in the previous talk, the real usability of monsoon prediction is in the regional predictions, especially on sub-seasonal scales. So we have just started intercomparing our models and trying to understand the predictive skill of active and break phases before going to the intraseasonal scales. And this is summary of my talk. Thank you.
Thank you, sir, for your insightful talk. May I now kindly invite Dr. Ashok Karpuri to deliver his talk titled Monsoon Prediction and Predictability Beyond the Usual Suspects.
I thought there was a tea break, right?
He is already served, sir.
Okay. So thank God I'm in the office. I was just about to go for 5 minutes. Okay, give me a minute, please.
Dr. Ashok Karpuri is a professor at the Center for Earth, Ocean and Atmospheric Sciences, University of Hyderabad. His research spanned tropical Indo-Pacific variability and its global impacts, monsoon theory and variability, seamless prediction, Earth system modeling, climate change, and the extreme urban events.
Is my presentation clear?
No, sir. Could you please share or?
Oh, okay, 1 second. Sure.
Yes, sir. We can see
Okay.
your
Good.
Sir, could you please make it as
Yeah,
a
1 second. Just give me a second. Yeah, is it okay now?
Yeah, yes, sir, yes.
Yeah, thank you for the kind introduction and invitation. So this talk is not so much a science rather than touching several points. I would urge you to bear with me if it's a bit looks a bit spread too thin and wide, but because we're talking discussion, we're discussing on various aspects, I thought I'll touch all the aspects. And while I focus mostly on my work, it doesn't mean that, but this is more of a representative, presentation. A lot of work is going on similar lines, and we have to come into a cohesive, what we need to do in future. I think all of these talks will obviously feed into the report. Yeah, we all know that Indian monsoon, the dominant variability is in intra-annual variability, as we see from several pictures like this, and mostly driven by El Nino. However, as we have seen in several talks since this morning, it's not just intra-annual variability, but we also, to some extent, we pay attention to intraseasonal variability, where we started predicting on extended range, scales. But there is transience also. Apart from stochasticity, there is the monsoon depressions that we talk. They bring in a lot of rain to many parts of the nation. So what we tend to do is we isolate impacts on various time scales, and we do not take them together, even when we give a forecast. So we tend to focus on seasonality, seasonally average thing. But when you are taking the biases in all time scales matter. In the morning, Surya also was showing some of these aspects. So what we need to do is, if you take the another aspect is the linearity. We tend to put everything in a linear sense. El Nino, La Nina, similar type of impacts on all time scales. But this is obviously not the case. For example, when we take this, just take El Ninos. El Nino and El Nino Modokis, there's different type of impact depending on where you are in the nation. And even when it go for the monsoon depressions, this recent paper tells you that the footprint and the spatial spread and magnitude on depressions versus low pressure is different. So how good your model is capturing these nuances on this high frequency scale. And when you come to intraseasonal variability, the impacts are different, and there is more non-linearity. For example, if you see the El Ninos, if you see that El Nino and La Nina figure A and C, there is almost a similarity in break days. Both red color is negative. But when you come to the active days, the La Nina impact is not so dominant as El Nino. During El Nino, you see a big deficit, but La Nina's, the impact is much smaller. You can see. So there is some sort of non-linearity. And unlike intra-annual scales, the El Ninos and El Nino Modukis, the impacts are almost similar. And we talk of this lead-lag relationship, and nowadays we talk of the post-El Nino effects and all. So all this sort of thing tells you is the evolution of not only intra-annual variability, but when you talk of the impacts post-El Nino at all, it may be something we're capturing about the decadal variability, decadal evolution, background changes in Pacific, and similar signals in Atlantic too. We need to pay attention. And the weak, almost nil correlation, the Indian Ocean dipole and Atlantic, these sort of things, you have a lot of impacts, as Behra-san showed us. Another aspect is the Atlantic zonal mode. Vijay from INCOAS, who's my PhD student, has done some work on, and IITM too, a lot of work has been done. The impact is very clear on intra-annual variability, as well as if you see the bottom two panels, the transients, the monsoon depressions, how the two phases of Atlantic zonal mode affects. There's clear distinction. But again, if you come to intraseasonal variability, some of the analysis done by Vijay shows that there is absolutely no impact whatsoever from AOZMI. This needs to be examined. And there is a sampling issue also. When they take the Atlantic impact, the impact seems to be changing over multiple decades. So in summary, most of the drivers affect the climate, climate at a place, events, intra-annual variability too, on different time scales. For example, this Chennai extreme event, we all know. So some of our work by one of my PhD students, Boyaz, the 2015 case was sort of a benchmark in multiple aspects and multiple drivers. For example, it was due to extreme El Nino that happened, and El Ninos in December caused more rainfall over in Northeast monsoon in this winter rainfall. So that was one factor. And the warming Indian Ocean, that played a major role. These two. And third is the urbanization. Later on, we did several experiments. Urbanization also contributes significantly to the extremity of the rainfall. So it's not any of these parameters that we miss or forecast for that event would have gone wrong. And add to the complexities, the decadal variability, Pacific decadal oscillation, these sort of things are also playing a role in weakening the teleconnections or exacerbating them. These things have been there even on millennial timescales as some of our works rules, but as far as intraannual variability is concerned, definitely decadal variability is playing a big role in stopping, exacerbating the teleconnections. And one interesting paper with Professor S.K. Das, he, at least in this model, they find that the snow cover seems to be a big impact, more impact as compared to the sea surface temperature variability, and it decides more of climatologically seasonal evolution. Snow cover is much more important. This is a very interesting paper. While it may be sort of an exacerbation of the impact of snow cover, definitely we need to pay more attention in terms of observations and modeling. And the role of weaker drivers and a stochastic but combination that suddenly playing a big role is from Nagaraju's group in Rourkela. They talk of this role of only in August there was this strong Rossby wave activity. Ideally, when there is this Rossby waves that come down, jet stream moves, actually this synoptic systems post-break synoptic systems do form. Here it was slightly a different way. There was a weakening of this transient activity, but most of the systems confined to low pressure rather than depressions, but they're 12 in number. And there was the activity of Western Pacific. You see this theater is so big as far as even a single event is concerned. You have to be able to predict all these factors. And decadal variability certainly matters on droughts. At least we saw in Saudi Arabia, and I'm sure over India too, we should explore this, how the climate change decadal variability play a major role. Importantly, we see now that the prediction skills are improving. Even in India, we have extended net prediction. And this nice paper, the summary, let me just give you a summary of this. It tells that there is skill, some minor but significant skill at 14 days, but that's not stochastic. Okay, there is a mechanism that it's significant, statistically significant. And so the models are able to capture the mechanism, high frequency variability. So we have to see how good the seasonal prediction models are capturing the transients. So that's sort of seasonal prediction and transients that may sound a non sequitur, but definitely can we see how long we are able to capture and can we push that envelope beyond extended range? This is again Sahai's paper. Sahai's group has also done a lot of work, both in terms of statistics, AML, and model development in this aspect. So then it comes to biases. A lot of biases. What I have been telling is biases cascade up spatially. If you don't simulate your monsoon depressions well, the seasonal rainfall will not be captured well, and so on and so forth. In terms of both spatially and temporally too. Then the question is, we're of course improving resolution and doing very good data assimilation. We're trying to get new data, but we have to also focus on biases in not so important drivers such as Indian Ocean dipole or even Atlantic, which we do not seem to pay much attention. So we have to understand that and see their our ability to predict them, the predictability across the models. Can we document these aspects? And of course, the drivers do change, as Behra was saying, and so it's not only decadal variability. Sorry, the context here is the driver changes from the location. For example, Northeast ENSO has no relevance, not much, but El Nino is important elsewhere. So these are the factors that we have to focus when you talk of local prediction, which IMD is nowadays doing. So one of these examples, as Behra was mentioning, Dr. Behra was mentioning, we are talking of AML, IATM to doing a lot of work, and Dr. Ravi Nanjandaya's group, Professor Ravi's group is doing a lot of work. So some of this work, for El Nino's, a lot of work. One paper that we are working with a colleague in China is improving the ENSO lead prediction skills with a deep learning model. Most of you know these how these things do work, transformative models, and so on and so forth. So important thing is, are you capturing the physics and the bias corrections that you're doing? Is it based on physics? So this is very, very important. For example, this CTEF net, my friend Peng and student Shi do, the skills are quite good if you see as compared to any GCM after improvement up to 18 to 24 months. There is a significant improvement. And the improvement does come because you're correcting the biases based on the physics, and the physics is really based on, I mean, it's capturing, the neural network is capturing the observational skills. This is, I mean, observation-based, physics-based improvement. This is very, very important, the so-called sensitivity. So these aspects, and there is many, many tools that are available now with which we can try improving our models, the model predictions. So this is the physical precursor, how the how the models are the tool has been able to capture this. And sometimes you may come up with some new mechanism which is real or which may not be, but definitely this is an opportunity to find other new mechanisms also. Another important aspect is we talk of multimodal ensembles and APCC. Everywhere we talk of multimodal prediction. A recent paper we published by Raju Pathak, now he's in Singapore, from KAUST, we did this work from the point of climate change context. But this applies to seasonal prediction also. We use multiple models, 50, 60 models to give you a forecast, a prediction, projections. But the issue is most of the models are similar. From a parent model, one single model, there are 3 to 4 models, and the biases in the original model percolate into the other models. And the skills that you get, or the projections that you give, they may not be really the uncertainties that you think you reduced, may not be that because you have used same set of models. So maintaining a diversity of models is very, very important. This is the message of the slide. And if you see the commonalities that cause biases, this is some of the aspects that you see. Many of the models have, for example, atmospheric models in this set of group in CMIC 5, 12 models have similar atmospheric, model and resolution, ocean model, chemistry. And as you come down, you can see where you need the diversity. And some of the work, many people, including us, what we did, if you have, even if you have 1 or 2 bad models, your MME skills come down. So based on your physics that are you're interested, be it INSO or anything, you try to reduce your bad models, then your MME would improve. So what we should be doing is revisit and try to identify unknown drivers at local scales for weather and climate. And if you correct your weather skills, then climate would also improve. And then, of course, a set of how you classify them and all, it's up to you. Then one thing today, we also talked about this non-stationarity, right? So if you think that PDO plays an important role in your droughts, and but you cannot in the seasonal prediction, when you're getting anomalies, you have only so much of, you start with some initial condition and you go, and when you get the anomalies. So how do you reduce the non-stationarities? One way is as simple as taking a 20 years short memory climatology. Maybe then that should take care of this non-stationarity. And so on and so forth. This may be correct, but this may not be. And today we'll be hearing a lot from IITM and Subodh and Chaudhary and all people, and Kosaka-san's nice talk, and all the talks we'll be hearing many more interesting ideas, and we will see what are the things that we can be sort of pull it in a new direction. Most of these things more of an engineering exercise, but we should pay attention to the science also. As Professor V.B. Rao says, theory is most important. Definitely, I think I missed one of the slides, or this Nagaraju's Rossby waves. These are easy to predict. Based on theory, instabilities, my Govardhan's work, my student Govardhan's work, and many. If you can predict instabilities, can you use those as a predictive tool from the models and sort of a theoretical, hybrid theoretical and dynamical things? Very simple. We can explore that. And of course, improving the model. Today, Surya talked of microphysics, and we have Kypex data. So maybe we can tune the microphysics based on the observations. These ideas are not new, but just wanted to collate them and bring it to your attention. Thank you very much.
Thank you. Thank you, sir, for your talk. May I now kindly invite Dr. Sheelan to deliver his talk on decadal modulation of monsoon teleconnections. Sheelan, sir, is the project director at IATM, where he leads the climate variability and prediction group. His research interests include the development of decadal prediction system.
Morning, everyone. I'll be talking about the decadal modulation of monsoon teleconnections. And if you look at the history, IATM in 1994 reported the decadal modulation of Indian summer monsoon. So what you see in the left, it's a percentage departure from mean for different decades, starting from 1981 to 90, or 1871 to 80. You can see that the decadal modulation is very clear. So now this has been an important topic. If you look at the long-term time series of Pakistan 94 or Sondagate 2008, which is extending from 1800. So you can see the decadal signals, and if you can decompose, if you can see the power spectrum, you can see the signals peaking at intraannual and the decadal at different scales, and also a multi-decadal time scale. So this is seen in both the time series. And if you decompose these data sets using empirical mode decomposition, you can see that the different modes, like intraannual mode at 2.7 year and 7 year, and you can also see at 2-year peak, which is explaining about 7% of variability, and also you can see one at 26 year and then at 65. And this, the multi-decadal signal explains more than 7% of variability. So now, if you look at the multi-decadal variabilities well known to us, and you can see this is the Atlantic multi-decadal variability, and which is the decadal warming and cooling of the North Atlantic. You can see the north of equator, the basin-wide warming showing the positive phase of the AMO, and similarly the basin-wide cooling during the negative phase of AMO. And if you look at the time evolution of the AMO, you will see from 1900, you can see the negative AMO and then positive phase, and then again you can see the duration and amplitude of the AMO is decreasing compared to the previous period. And if you look at these AMO, the extratropical and the tropical components, you can see them like this. So both of them interact with the global climate in different ways. The one through the tropical connections and the extratropical one through the extratropical connections. And similarly, you can see here the Pacific decadal variability. So this is the positive phase of the Pacific decadal variability, and you will see the large negative assessed anomalies in the northwestern Pacific region, and you will also see the positive anomalies in the eastern region, and this is the northern part of the IPV pattern, which is called the PD. And if you look at the extension it has over the tropical region, you'll see something similar to what you see during the El Nino time. But if you look at the the time evolution, and it is relatively smaller than the 60 to 70 years periodicity Atlantic multi-decade variability. It is about 20 years of variability. And one more thing, if you look at the IPO phases and the PDO phases, there is a component, for example, and you can see there are phases like all these phases. The beginning of the AMO coincides with the beginning of the PDO phases with a lag of about over 10 years. So that closely suggests that there's a possible relationship between the AMO and the Pacific variability. And these are very important if we look at the IF file, like IAMAS file of the Indian monsoon rainfall, if you regress it over the global SST, you will see that most of the dominant multi-decadal or decadal modes of variability in the ocean. For example, the warming what you see as part of the decadal PDO and the warming you see as a part of the AMO, and also what you see here, the cooling what you see as part of the decadal ENSO, and also you see a cooling over the Indian Ocean region. See, these all contribute positively to the Indian monsoon rainfall. So, say during the warm phase here, cold phase here, cold phase here, you will see more rainfall over the Indian region. And if you look at the Indian Ocean SST, so that this time series shows the level filtered, the sea surface temperature of the Indian Ocean, which is red, the PDO, which is blue, and the KMO, which is green. And what we notice is there's a coherent alignment of the Indian Ocean SST with the Pacific PDO. But if you look at the recent years, that the relationship is sort of reversed. And similarly, you can see the AMO, but in the recent years, they are opposite, they're negatively correlated. And if you look at the importance of PDO, here the Indian Ocean SST, if you below the effect of PDO, so that is the level, you will see, and there's a clear difference from the green one, which is the Indian Ocean SST. But in the recent years, you see, even if you remove the effect of PDO, the relationship is the SST evolution of Indian Ocean is same. That suggests that the PDO relationship is not really affecting the variability of Indian Ocean in the recent years. On the other hand, if you look at the North Atlantic oscillation index, which has significant the negative correlation with the Indian Ocean SST evolution. Now, if you look at the correlation here, you will see very clearly that here the red one is the correlation between the Indian Ocean SST and PDO, which has been significantly positive since up to 1990s or before. But see that period after the 1990s, and then it is significantly negative in the recent years. Whereas if you see the Indian Ocean SST and the North Atlantic oscillation, so it is now in the recent years, it becomes significantly positively correlated. And so that's some of the things, what could be happening in the recent years, which in the Ocean and in the monsoon rainfall decouples with the well-known climate multi-decadal climate modes. And here is the figure, which is, here precipitation regressed over the AMO index. AMO index is the average SST anomalies over the North Atlantic. But you can see which is totally correlated with the Indian monsoon rainfall. And it's all you can see Sahel rainfall, it is more significantly correlated. But you can see this, and similarly, you can see the wind, the 850 HP wind, reduced on AMO, you can see the stronger cross-equatorial flow, and similarly, there is the convection, 500 HPA vertical velocity, you can see the large convection over this region induced by AMO, and this is the upper atmospheric temperature, which is 200 to 500 HPA average air temperature. You can see during the positive phase of an AMO, you see large warming over this region. Now, if you have a warming over the land region and cooling over the Indian Ocean, it can because of the temperature gradient, so the gradient can drive strong monsoon currents. So that is how you get more rainfall over the Indian region during the positive phase of PDO. Positive phase of AMO. But if you look at the AMO Indian summer monsoon rainfall relationship, it's a running correlation, you can see. So this relationship is very significant, and it persists for a long time till the 90s. But from 90s or late 90s, so this relationship is, the AMO, you can see they both are going in the opposite direction. So AMO is in a positive phase, but the Indian rainfall was in a negative phase, and it's slowly beginning to form positive. And you can also see that this only this relationship between AMO and monsoon rainfall weakens. For example, so this is the long-term relationships. So you have a positive relationship with the AMO, the Indian summer monsoon rainfall. But if you look at the different periods, for example, this is during the positive phase of a AMO, you can see there's the positive relationship is over large regions here. It's a positive here, and if you see the next negative phase of a AMO, still I have the positive correlation. Whereas if you see the recent years from 1995 onwards, if you look at the AMO relationship with the rainfall, so there is a negative correlation, very significant negative correlation over this region. So, and that recently found that the temperature change essentially changes over the Indian Ocean, which is different from the previous periods. This is the first phase of a positive AMO, and this is second phase of a negative AMO, and this is the third period of a positive AMO. See, that's a contrast. So one thing is that there's a sensitive warming trend. So possibly the warming trend may be causing or weakening this relationship with the large climate modes. And something like the Indian Ocean warming, see, co-occurred during the recent AMO warm phase, we can see meridian temperature gradient, which we can see regional had recent large-scale monsoon circulation precipitation. Also, the tropical high, which is also playing an important role in weakening the relationship. Similarly, we look at the variability. So this is the AMO AMO and its response on the Indian monsoon. But many times, if you look at this is the first mode of variability, and if you look at the Atlantic second mode of variability, you will see a tripod pattern of variability. So which is not similar to this. So there's a change in the warming pattern, but then when the warming pattern slightly changes, what you see the response, the response on the Indian monsoon is in contrast. But you have a negative the relationship. So this may be playing an important role in the relationship between Atlantic and Indian monsoon. Similarly, the relationship with the Pacific variability PDO, and during the positive phase of PDO, the negative rainfall over the Indian region, and this is another. And during the negative phase of PDO, you have positive anomaly. Similarly, this is what you see in the environmental anomaly, El Nino and La Nina years. And similarly, when they co-occur, the warm phase of PDO co-occur with El Nino, the impact is much more. Similarly, the cold phase of PDO co-occur with the La Nina, the impact, you see the countrywide, the positive anomalies. And the reason what you see is the normalized Indian rainfall trend. If you see from 2000 or so, you see large positive trends in the rainfall over the northwest region. And so this is from different data products. So all show consistently the increasing rainfall. Similarly, you can see the soil moisture increase. And also you can see the relationship is very strong over the entire region. And this also is seen, affecting the dust over this region. And you can see, so this is very attributed this the recent trends to the westward extension of the Indian Ocean warming, and this westward extension extending more westward and bring more rainfall over this region. But what is more the problematic is, so if you look at the projections, so the projected SSTs are showing much more westward extension and the westward extension of the IT season. So that is strongly suggesting that the Indian Ocean warming could be one of the important factor weakening the relationship with the multi-decadal the oscillations. So we can now see, so this study by Coordinator, so they took the different models, say 10 dry model and wet model, which is getting the mean rainfall over India, and they found the difference, and they found the strong connection between the pattern of PDO and El Nino, the Equator Pacific and the North Pacific evolution in the monsoon rainfall. And they argue that the PDO representation in models is very important. Without the IPO, the standard deviation weakens. So the predictable source weakens. Similarly, they found experiments with positive IPO and negative IPO, and they found if you look at the positive IPO impact, the chances of precipitation decreases from 75 to 54, and the chances of extreme drought condition increases from 10 to 32, and similarly the chances of extreme wet seasons reduces from 10 to 1. So similarly the IPO. So these strongly suggest that the representation of the PDO model is very relevant for predicting monsoon rainfall. So this also another study by Chidaitel. So how the ISMR is responding to PDO in the current climate models. So you can see the observation that the different model. You can see that some models, for example, about 50% of the models show some sort of a relationship with the observed relationship, but see there are many models, about 50% of the models, the relationship is misrepresented. So this is going to be one of the important challenge for future. And see another one is, see like this is the AMO lead relationship with the SST over the North Pacific. You can see there's a strong relationship, and this is how the relationship evolves. The 1 year, 2 year, 3 year, like up to the 10 year. So you can see. So these relationships are really these relationships established through the subsurface processes. So you can see here, this is the evolution of PDO, and this is the evolution of AMO, and in the Pacific, the subsurface temperature anomalies in the more water pathway that is evolving very closely with the AMO. So that is one challenge, because there is the lag relationship with the PDO. You can see this is how the relationship with Pacific develops. So this is going to be an important challenge, especially for predicting summer monsoon rainfall, because the connection between the AMO and PDO, which is very important in representing the PDO right. If PDO is not represented well, it will have a negative impact on the predictability of the Indian summer monsoon. Thank you.
Thank you, sir, for your talk. Next, let's move on to the next talk. May I now kindly invite Dr. Rossi Matthew to deliver his talk titled Monsoon Rainfall in a Changing Climate, Trends, Teleconnections, and Prediction Across Scales. So, over to you.
Thank you all. Thank you for this invitation, and it's a delight to see all this discussion on monsoon variability. Let me share my slide. Can you see my slide?
Yes, sir. Yes, it's visible.
Oh, perfect. Yeah. So all the discussion until now has focused on monsoon variability. My presentation talk is also focusing on monsoon variability, but there's a difference. So far we focused on the role of ocean-met conditions on the monsoon variability. Yeah, large-scale features, teleconnections, intraseasonal variability associated with ocean atmospheric conditions, a bit of aerosol, all these factors. So these large-scale conditions are quite important. I agree. At the same time, Dr. Ashok Karumuri was talking about those less known drivers of monsoon variability, which we need to focus. And probably they add a huge impact on intra-annual and intra-seasonal monsoon variability as well. So you see a few characteristics that lead to this kind of monsoon variability. So we will talk about this in brief. For example, land use, land cover changes, irrigation, and all those factors on monsoon variability as well, because they also play some role. These are mostly human-induced changes. And we will also see what kind of tools we can use in terms of observations, in terms of modeling, in terms of AIML, and also how, along with changing or impacting this variability, how humans can also be participating in understanding the monsoon through citizen science activities. So this is an interesting plot. This is from IITM IMD homogeneous Indian monthly rainfall. You can access this image from the Monsoon online website hosted by IITM. And this is about 154 years of monsoon in one snapshot. You can see the blue colors are the wet years, where it is about 10% of the mean departure from the mean, and the red colors or the red bars indicate the dry years, which is below the 10%, and the normal years in gray. Yeah, and there is a long-term running trend. You can see that gray curve going like this, showing the multi-decadal variability that Dr. Sheelan was also talking about. So in this, we can see, overall, over a long period, there have been periods of wet and dry periods and all. But if you look at the recent period, we can see that there is a slump in this trend, which indicates kind of, if you look at all India rainfall, mind you, this is all India rainfall average for the entire country based on the political boundaries. So if you look at that, even there, we see a kind of reduction in the total amount of rainfall despite the multi-decadal variability. And if you look at the recent period, at least from here, that is around for the last, I think, 26, 27, or up to 30 years, we did not have a significantly wet year. There are some years when it reached, close to 10%, but otherwise not above that. Yeah. So we see a lot of dry or drought years. IMD doesn't use the word drought anymore, but we see a lot of rainfall deficit years. But this also tells us that it is important to look at regional variability as well. Now, if you look at the predictability and predictions of monsoon, from the start itself, Dr. Surya Rao was talking about how the predictability of the monsoon can be harnessed and how the recent models that IATM and others use have been improved. I would like to you to focus on this interesting picture. This is a hand-drawn picture by Subodh Saha with an octopus with its tentacles. What this shows is, different environmental conditions from different regions, like soil moisture is there, snow is there, North Atlantic oscillation, which Sheelan was talking about, PDO, IOD, different factors that affect the monsoon variability, including the intraseasonal variability of monsoon. So what these studies show is that if you are able to capture the interactions, you can scale up the forecast skill to up to 0.8, yeah, which explains about 70% of observed interannual variability. And of course, there are many attempts which shows that, okay, the recent multimodal CFS2, we are able to capture a lot of this, particularly arising from oceanic variability by improving the both the initial conditions and also how the ocean atmosphere coupling is captured by this model. So this is a comparison between the earlier version of CFS and the later CFS2. Now, that showed that ocean conditions are quite important. Ocean coupling is also important. But what kind of ocean observations do we have actually? Yeah. So if you look at, we know that Indian Ocean conditions are very much important. IOD is important. And if you look at this figure, I will try to zoom in. We have seen a lot of ups and downs in observational networks. So as part of the Indian Ocean Regional Panel, we had done an assessment and redesign of the observation system and all for the Indian Ocean. But during COVID, a lot of these observations, for example, these are Rama moorings by end of 2019. But by after COVID, you see that 0%, almost all of this moorings stopped sending that information, especially Rama moorings and also India's Omni moorings as well, which have potentially had a huge impact on how we predicted not only monsoon, but also other extreme weather events during the last 3-4 years. Now we see it is recovering a bit. Some of these moorings have been re-employed and in place. But this shows that we need consistent ocean monitoring systems. We are far away from that the optimal number of ocean observations that can provide accurate weather and seasonal forecasts. Yeah, and here is a study showing that why ocean moorings are important. They show that, okay, the Pacific moorings are important. The Indian Ocean moorings also might be potentially important. So these are important for all sectors: agriculture, water resource management, fisheries, and all. So it can be overly stated that ocean observations are important, and this requires regional partnerships. Not only just one country alone cannot establish these kind of ocean observations across the Indian Ocean. This is an example of regional partnership where US NOAA moorings deployed from India's INCOIS research vessel. So we need more of these partnerships, which means international collaborations. Which means that for a ministry like Ministry of Earth Sciences, we cannot confine ourselves to a set of observations without collaborating with other organizations. Now, other than observations, there are other tools. We all know about the progress in IAML in the recent years. I would say there has been attempts in forecasting US rainfall for at seasonal forecasts, and they see that machine learning based models are capable of competing or outperforming existing dynamic models, even from the multimodal ensembles. And they use sea surface temperature, velocity potential, the winds. So not just oceanic conditions, but also atmospheric conditions for multiple machine learning methods. And they're able to, give seasonal forecasts which outcompete many of these existing dynamic forecast models. And they also show that we can interpret. We don't use IAML not just as a black box, but you can also leverage the capacity of interpretability methods to identify the relevant physical processes underlying in these models and data. Now, that is, even this is like a few years old. The recent approach is to combine machine learning with physics-informed conditions. So you have a machine learning which goes through all this data, ocean atmospheric data, but also you constrain with the physics that we know, the mass conservation and many other physics that is important for this ocean atmospheric coupling and the weather variability. There have been preliminary attempts from, for example, B.N. Goswami, which indicates this is preprint still. I thought this would be out in the public by now. It's yet not accepted. They show that there is potential skill and lead time of monsoon forecast with IAML just by leveraging ocean conditions. Yeah, so they didn't explore all these multiple variables and multiple models, but with single model and with just global ocean conditions, they were able to. They claimed that they could get a good lead time. That lead time is huge, 18-month lead time. Yeah, but we need to be, probably the current day models and physics informed is the way forward to improve this kind of attempts. Now, some of the earlier talks focused on the monsoon variability, but we have to be aware that monsoon has a huge regional variability. So if you look at all India rainfall that I showed in the first slide, it won't represent this regional variability. It is just an average based on the political boundaries. So this is an example of the forecast in 2023, which shows the regional distribution of the rainfall below normal, normal, and above normal. You can focus on the red and blue colors, and also the green colors. And this is the observed for that year. You can see the disparity is huge, even though on the all India rainfall level, there has been some skill, and even for that year, it is close to the observations. But when we look at the regional variability, which is actually the most important factor for decision making, we are unable to achieve that. So what connects to that regional variability? Again, we talked about a lot of ENSO monsoon variability. But here we show that this ENSO monsoon variability also has a regional, is totally different at regional scales and also temporal scales. So different regions have different teleconnections with ENSO. That is one thing. And also across periods, this ENSO monsoon relationship is changing. So I would bring your focus here. So this is 40-year chunks. You can see the earlier period, the ENSO monsoon the teleconnection is not that strong in, for example, some parts of central India and all, but stronger here and all. But if you look at this period, it is totally different. This, especially the central India, this region and all, the correlation is quite strong. Here again, it is weak. So if you look at this time series, averaging over South India, North India, Central India, you can see that. So this is strong correlation. North India, the correlation has increased over time, which means that there is more predictability for predicting North Indian monsoon rainfall. While South India, the correlation is still strong and has remained stable. But if you want to predict the Central India rainfall, it is close to zero, especially in the recent period. So we have to be mindful about this, not only regional variability of monsoon, but also the teleconnections which influence on this regional variability and their variation over time. So are our models able to capture this? So there I come to the changes in mean and extreme rainfall trends from a climate change perspective as well. So this, from our Nature Communications papers, 2 papers cited here. The blue shows where the rainfall has declined over time, and this is for this has been updated as well. So all these regions show there is a decline, those blue colors. At the same time, across the monsoon core region, there is an increase in extreme rain. So if you pick this monsoon core region, you can see the total amount of rainfall is declining over time, while extreme rains are increasing. So this also affects the water and food security, especially over the core monsoon region. For example, it also means that there are more long dry spells, intermittent with short spells of heavy rain, and this rain water doesn't get absorbed by the groundwater. It doesn't recharge the groundwater. It either flushes out to the rivers and to the sea or gets evaporated. So there I talked about how it interacts with the land surface groundwater also, right? So here I come to these multiple factors. Sheelan was talking about Indian Ocean warming and also how it might be changing over time. So this is a normal, So this is how it normally is. Not only the land surface, but also the troposphere above that remains warm during the monsoon due to the latent heat flux and all. So that kind of leads to this monsoon circulation. But if ocean is warming pretty fast, that can weaken this. But recent studies by Jin and Wang points to a potential possibility that, now in the recent period, the land is also warming. So it's a competition between ocean and land as well. But there are other factors, aerosol impact and all, Bolasina and many other studies have shown. I'm not getting in depth on that, but generally they show that these kind of studies show that, there is more aerosol in the South Asian region, which can suppress the land warming and can weaken the same monsoon circulation. So multiple factors, ocean warming is there, aerosol impact is there, and recent studies show land use changes also. So this from Subimal and Paul et al. From IIT Bombay, they show that, with the land cover changes can correspond to many of the changes in rainfall, the reduced changes. So this correspond to the brown colors correspond to the reduction in rainfall. So we need a comprehensive study. So each study, like my study or aerosol study or land use study, this look at this, especially the modeling experiments. Look at these factors separately. We need a comprehensive study that puts all this together in one framework. So there, land use changes are quite important. For example, this nature study shows, which is based on Amazon, but shows that recycled rainfall is quite important. So if there is a lot of rain in one region, there is plant evapotranspiration, especially if there is a lot of vegetation. it again, results in clouds formation and resulting in rainfall in that region itself. Yeah. So this can contribute to 10% or 15% or sometimes 20% in some years, recycled rainfall within that monsoon region. And we know that these kind of rainforests, including India, are important for this kind of what we call the water pump. And this has shown to be important for the extremes that I showed earlier as well. This is again the same picture, updated picture. The red colors show the extreme rainfall. So what this study shows is that different contributions, we track different contributions from Arabian Sea, Bay of Bengal and all. But Central India contribution is close to 30%. And this is especially during the September period for the monsoon, which means that this recycled rainfall also contributes to extreme rains as well, not just total monsoon rainfall, but extreme rains as well. So we need to factor in all those aspects in our models, in our observations. So further studies shows that, so I briefly touched about groundwater and all, there is a lot of, due to that decline in that core monsoon zone, there is a lot of groundwater extraction. So these are pictures from the wells, and these are from the satellites, which shows potential groundwater extraction and irrigation. So a lot of water is pumped back from the ground to over to the earth surface, and which again comes back to this as recycled rainfall, and also changes the monsoon circulation, interacts with the local weather. We also see potential impacts due to major human interventions. So if the runoff for India from the rivers is around 1,800 billion cubic meters. Yeah, that's the annual runoff from rivers, which comes from the monsoon. After this, the proposed river interlinking is supposed to kind of divert or exchange 18 cubic billion meters of water on an annual level. That is about 10%. 10%. Yeah, if you take all of this. So this is a very ideal scenario from the proposed Himalayan and the peninsular links. So if all this happens, for example, it can affect the monsoon again so this is one basin. So from this basin, we are transporting water to the other basin. So it will change the evapotranspiration in this basin, but also change the evapotranspiration in this basin, and there are cross-basin interactions as well. So using causal theory, this paper looks into that. So a part of this has already happened. So we see that different kind of land, forest usage, and also river usages are interacting with this complex monsoon system, and we need to understand that. And there is strong local and regional variability. This is my last slide, where despite those human impacts, we also see that humans can also be participating. The citizens, not just scientists, they can also participate in monitoring these rains, understanding the changes. For example, this is a log from a citizen science network, which shows the extreme rainfall. You can see 190 millimeter per day, which IMD or any met agencies or even satellites did not measure. Yeah, and they connect these kind of citizens sciences, they connect it to river discharge as well, and they put it in the newspaper bulletins. So this kind of, we need to work together, take up whatever opportunity, understand this is a complex system, and hope that monsoon can be predicted better. We can understand the variability better in such a kind of system. I see that AIML methods and other tools and better observations can help us in doing that. I've also been part of this. Scientists can be part of these kind of activities. So with that, I conclude my work, my presentation, which shows these kind of intricate factors we need to consider as we move forward with monsoon forecasting. Thanks a lot.
Thank you, Dr. Roxy, for your insightful talk. Moving forward to the next session, may I now invite Dr. Subodh Saha to deliver talk on recording the predictability of Indian summer monsoon rainfall. Dr. Subodh Saha is currently serving as scientist at IITM Pune. His research expertise lies in understanding the Indian summer monsoon with a particular focus on its complex interaction with land surface processes and air-sea interaction. Over to you, Dr. Saha.
Thank you. I would like to thank organizer for giving me opportunity. So let me take you to some history of monsoon forecasting. So it started, formal forecasting started after the maybe 1876, 1878, and then Blanford was the first person to issue some forecast. Interestingly, based on some land surface process snow. And then after that came Walker, who gave these teleconnections, the concept of teleconnections, and then how discovered the this southern oscillation, which is later became associated with ENSO. So these are the beginning. And on the other side of the world, there was some theoretical development was going on. Reactness, he gave us the primitive equations. Then came Richardson, who tried to forecast using these equations. And then, the idea was that we can not only predict weather, but we can also control it. So it was basically the idea was to use it as a weapon, right? So then came Newman, von Neumann. He was also thinking that you can have a forecast and you can use it as a weapon. And then he was interested in doing in a computer. And then, there was an ENIAC computer. And there is a great enthusiasm that we can use the computer and then have a very accurate forecast, and we can use it as a weapon as well. But the serious blow came by Lawrence in the 60s, 1960, and then we came to know that we cannot predict more than so weak. So it was a serious blow to all these ideas, and then came Charney and Shukla. So they said that no, we can predict some monthly to seasonal scale. So what started by Walker and all that was proved by actually the theory in 80s. So it is not very long ago that we came to know that we can predict also season quite in advance. So what we understand that we have a not very different from what time of Gilbert Walker and all those discovered, that we have a predictability of atmosphere in weeks, and then you have a land which is up to a month, and then you have ocean for longer predictability, longer time scale. And also we know that those predictability is flow dependent, means that how your predictors are aligned, it will change with time, right? So this is a very idea as they develop. And then we can summarize, we can think of those predictors, how they affect monsoon or any weather system in terms of external component, which is the predictor is like ENSO, IOD, AMO. And then you have an internal component like local variability, like subseasonal or atmospheric mode. You can have also local oceanic or land surface mode. And then there is a question whether they can, these external ENSO predictors, which are lying far away, they can interact with these local modes of variability. So there is a two school of thought. That one thought is that one viewpoint is that these predictors are ENSO, IOD, they interact with monsoon, and then internal component, what we tell the internal component, subseasonal component, they are basically non in the system. So there are several papers on this. For example, you can see here that although I quote that although low pressure system play important role in monsoon mean rainfall, but they may not be affecting the internal variability. Similarly, other papers also talk about mesos, that intraseasonal variability, they are actually not contributing much. And another viewpoint is that that well, we have a predictor like ENSO, and also we have a subseasonal component, and they have some close connections. So the idea is that a predictor alone cannot act; it has to act through those components, those subseasonal components, and then it's affect monsoon. I put an arrow both ways because sometimes we have seen, we know also that monsoon also can affect some large scale predictors like ENSO. So this is in this idea you have very large number of papers. For example, Goswami et al. 22 that they linked with North Atlantic SST, which is linked by some stationary view wave trend. Then you have paper Bora et al., which also talks about North Atlantic Ocean and then how it is connected with the monsoon through wave trend. And then you have another paper by our group that how seasonal and synoptic they contribute to monsoon variability, seasonal variability, and also they are linked to predictors. So coming to this one, this is very simple figure, but let me explain that upper panel, it is a correlation between subseasonal variance of all these bands and then ISMR. So what you can see that you have a maximum correlation on the synoptic band, and then you have a moderate on ISO band. Okay, so that means that synoptic system is contributing maximum to internal variability of ISMR. Okay, and then how they are related with predictors. So that you can see in the lower panel, like it is correlated with ENSO. So you have a strong correlation with ENSO also. So this tells you that those subseasonal components, they actually interact. They are influenced by predictors like ENSO, and then they result into monsoon variability, year-to-year variability. As I mentioned, Bora et al., they showed how North Atlantic, the upper panel showed North Atlantic SST is linked with a stationary wave pattern that comes along from Atlantic to up to the Indian region, and then they affect monsoon in a way that it extends the break period. So it is again on subseasonal time scale. They dominate almost half of the year, where you have a dry season, half is controlled by North Atlantic SST. And if you see today we have heard a lot of interdecadal variability. One more analysis here that if you see on different band of monsoon, of course Indian monsoon 2 to 5, 20 to 20, and 20 to 60 days, these variances are correlated with ISMR. Okay, but you see that synoptic band you have a lot of interdecadal variability. Okay, but they are always positive. 10 to 20 days, you have a strong interdecadal variability, but it is changing completely phase. From what we have 90, 30 to 50, it has positive correlation, becomes 70 is a negative correlation. So there might be very strong change in some predictors. What you can see in the lower panel, the difference, you have a very significant change in SST over PTO region, North Atlantic, as well as Southern Ocean. So that clearly tells you that how these subseasonal components are controlled by this large scale predictor. So they are basically interconnected. So it has been always a question in our mind that to what extent we can predict the seasonal monsoon. Okay, so we have a different kind of model. Sometimes we have a statistical model, sometimes we have a numerical model, a couple model. So we want to know to what extent we can achieve the theoretical thing, correlation in terms of correlation. If you talk, it can go up to 1 theoretical limit, but there is a lot of non-predictable things, like I mentioned Lawrence, that there is still not of chaos in the system, so you cannot predict everything. There will be always something you will lose. So what is the extent we can predict? And then the question is how we can estimate those predictability limit. Limit means what is the maximum we can do. So there is people have tried two ways based on one is the observation. You take observations and you try use different type of method and estimate what is the maximum level you can have. And then you have a model-based estimate that basically use the perfect model framework. So I will just go briefly one by one. The observation-based method, basically you identify your predictors, what are the predictors that can affect monsoon, and then try to relate or estimate their variability, covariability. So one study is by Sharma et al. What they try to do, that they, instead of taking indices, let's say Enzo, IID, all those, they take entire tropical basin and then some correlation map they create and then project the D20 anomaly, heat anomaly, heat content anomaly, SST anomaly, as well as SST. Three things they try, and then reconstruct the ISMR time series. Okay, so here you see the in 18-month lead time, you have a D20 depth. Using D20 depth, they have reconstructed ISMR, which is a correlation of 0.84. And the lower panel you can see at defined parameter like D20, heat HP is heat content, SP is surface temperature. So you can see surface temperature is giving less skill because SST you have a lot of contamination, a lot of noise imposed by atmosphere. And if you go in a deeper, let's say heat content, this is slowly very not much affected by atmospheric noise. You have a very good skill with 18-month lead. And if you link with SST, NO3 SST alone, you have correlation of close to 0.4. So this estimate tells, including all this SST information, ocean information, that you can have a predictability of 0.84. Okay. Now, another study that deals with here 4 predictor. You can see the 4 NO3, IOD, AMO, and PDO, which is used at a multiple regression analysis. You take this predictor that you consider they are the only main predictor, and then regress with ISMR, and with 31-year running window, and you can see clearly the red line, the covariability, multiple correlation is very 0.5 to it goes up to more than 0.7, and then it is really varying with time. Okay, and it is on average it is around 0.7. Now another thing is that as I mentioned that we don't know all predictor. We have only considered the earlier study only considered the ocean, but there might be other predictors also like land or CIS something or higher latitude regions. So we don't know many predictors. Okay, so in that context, how you estimate? So other idea is that the hypothesis, this is basically hypothesis that let us consider you have all kind of predictor, they are affecting your monsoon through subseasonal component. Okay, so let us use this subseasonal component and consider that they are mainly affected by predictors. And then if you use this subseasonal component and regress with ISMR, what you get is the blue line. Okay, so blue line. So what it is showing that this subseasonal component is a covariability with ISMR. It goes up to 0.9 and sometime in the 60s. So, and then it is average around 0.8. That is indicate average 0.8. So you can say this is about 0.8 is a predictability limit from observational point of view. Now coming to model. So model people have tried different model and different time. So what is the idea? Idea is that you consider the model is perfect. Okay, this diagram model is perfect, and you have a error only in initial condition. That gives you some divergence because of nonlinearity in the system, chaotic system, and this divergence is nothing but noise, and then ensemble average will give you the signal. So this way you calculate what is the signal, what is the noise. Based on this, people have tried to calculate with starting from ICTM. You can see the Kumar et al. Is 2005. So that time model had a negative scale. You can see it was a model, ISMR scale was negative, and then potential predictability was around 0.65. This is all this ICTM. Next generation model we had, people have tried like Rajiv and et al. That you can see blue line, green line, that is scale has improved, and then predictability is around 0.65 or so. So it is using concept of perfect model. But that is a problem that mentioned in various studies like Kumar et al. That when you use this framework, you have a sometimes you get a skill, actual skill more than what you have the limit, predictability limit. So how this is possible? Okay, because predictability limit, we think this is the upper limit, maximum possible limit. But when you go in an actual forecast mode, you get a skill more than that predictability limit. So it is a paradox kind of situation. Okay, so why this is a paradox? Because this is the paradox mainly we consider that this model is perfect. Only the initial error is the problem. But that is not the case. Reality, we have a lot of problem from, let's say, physics, dynamics, or numerical things, a lot of problem. So for this doesn't apply, or this is not valid every time. Okay. Similarly, our study with CFS, we have seen we have used this ANOVA method as well as perfect model method, and then you can see we have a 4 version of model here: quant, snow, MP, HY, and SNMP. So there, at least in 2 cases, we can see the skill is more than this predictability limit. So there clearly there is some problem with this method. So what is the way forward? So way forward is something we proposed like this, that what we want. We want to understand that given a forecast system, given a simulation system, what is the maximum skill one can achieve? That is the thing we wanted to know. So, and also you remember that this perfect model framework, it is only using model, and it has no relationship, no binding relationship with observation, right? So what we try to do here, that let's get the ensembles, subset of ensembles from this experiment, from any experiment, and try to relate with observation, try to get the correlation. So how we can do it? You create a lot of subset using combinations. For example, you have 16 member ensemble member, you can create subset of up to 22 to let's say 15, lot of combinations, and then you get a distribution of skill, real skill, and then find out what is the maximum skill your model, your system can achieve. By doing this, you can see the graph here. X-axis is correlation, and then y-axis is the subset in the members, and the dotted line is the minimum skill, and solid line is maximum skill. So you have a 4% of model skill starting from around 0.55 to 0.71. You can see this when you have a skill, as per skill, this whole distribution pattern is shifting to the higher side. So you can consider this is the limit what you can achieve by this system. It is around 0.8 with this model. And also, it is also considered that this is not the fixed thing. This is that if you have a model, improved model, the skill will improve further, and then also you have a higher predictability. So as per our current understanding that we have from observation point of view as well as modeling, that we have an upper limit of 0.8. We can go, and then there is a thing. So I stop here, and thank you.
Thank you, Dr. Subodh Saha, for your insightful talk. Now let's move forward. May I now invite Dr. Jasti Chaudhary to deliver his talk on are the multi-teleconnections increasing the complexity of Indian summer monsoon variability in recent decades. Dr. Jasti Chaudhary is presently working as a scientist at Indian Institute of Tropical Meteorology, Pune, India. He is widely recognized for his expertise in the predictability of Asian summer monsoon, Indian monsoon variability, and AFC interaction over tropical Indian and Pacific Oceans.
I would like to thank organizers for giving this opportunity. So, so far there have been a lot of discussion or talks on the different modes of climate variability, their impact on the monsoon, and history is known. Now, what is happening currently in the monsoon variability? So, are the multi-teleconnections increasing the complexity of the variability in the recent decades? So, when you look at this particular figure, you could see there are a lot more of these climate modes that are operating onto the monsoon in the interannual time scale, as well as decadal time scale, and in the global warming. So how these modes are impacting the monsoon are being given the path here. So I'm not going to go into details, but this figure particularly brings out the gap areas. Thanks to COSAC for providing this. And you have close interaction between Indian summer monsoon rainfall and East Asian and Western North Pacific. So strong Indian summer monsoon can modulate the East Asian summer monsoon, and then there is interaction between Northwest Pacific monsoon and the East Asian monsoon, and that can again influence the Indian summer monsoon. So this is a kind of tug of war among these monsoon centers, and these set of these monsoon centers can be influenced by the other teleconnections, which either can be from the tropical regions or can be mid latitudes. So those question marks represents some of the unknown pathways, like how can we the blocking can influence in different time scale. Maybe in some time scales we knew, and what is the complexity in the recent years? If you see the difference between the mean rainfall between before 2000 and after 2000. So what you would see, high rainfall over the western parts of India, northwestern parts, and then you have low rainfall over the eastern parts, especially in the northern side. And again, you have kind of high rainfall south of it. So this pattern wasn't being there before 2000. It is emerging in the recent years. As you can see here, a green one and yellow one, one is increasing northwest parts of India rainfall, and here is the eastern parts of rainfall. Eastern parts of India, the rainfall is decreasing after about 2000, year 2000. So, this pattern is going to be continued, and what are the climate modes that can really influence this particular mode? So, this is very important. Why is like India experiencing a dipole pattern of rainfall, and will it become more variable? So when you look at the contribution of the Northwest India rainfall to the total rainfall or India distribution, if you see, it is around 16% is contributed by Northwest India rainfall to the total rainfall before 2000, and after 2000 it is decreasing to increasing to 20 and then 22 in the recent years. The recent year means it is from 2020 to 24. It has been increased about 20. So in the on the other hand, in the central India rainfall is decreasing. The contribution is also decreasing from 35 to 33. So there is a shift of rainfall pattern against the historical norms. And then, so I'm going to concentrate only last 4 to 5 years, what is happening and how this dipole pattern is maintained, and what are those mechanisms and modes. When you look at 2020, so it is like more than 100% rainfall received over India. And then if you look at the modes of variability, so you have weak La Nina-like conditions in the Pacific. And one more mode we have is a PJ pattern, the Pacific Japan pattern, with intensified anticyclonic circulation over this region. And also we have a tropical Indian Ocean warming. So tropical Indian Ocean warming can interact with the Western North Pacific circulation, and then it can feed back to the tropical Indian Ocean, the mode what we call it as the Indo-Western Pacific capacitive mode. So there are two modes active, and one of them PJ or IPOC seems to be a dominant. When you have strong anticyclonic circulation over this region in the Western North Pacific and associated strong subsidence over this region, and then the associated westward propagating cold Rossby wave can have a strong divergence over this region and moisture divergence that lowers the rainfall. So the active IPOC or active PJ seems to be more dominant than the ENSO itself. Now, this active PJ seems to be again changed its path. So the anticyclonic circulation seems to be very narrowed down, and easterlies associated with that PJ pattern or anticyclonic circulation move towards the equator, and they match with the LHJ, and there is a strong convergence over that region, and we have a strong monsoon. So the single mode seems to be changing its base, and it is going to influence differently from one particular month to another particular month. This says that the teleconnections not only important for the seasonal point of view, also to the sub-seasonal point of view. So here is the strong divergence is seen in the July month. In August, it is a strong convergence. When it comes to the predictability or model skills, models are tend to predict strong La Nina-like conditions rather than what we see in the model. It was weak, and there was no strong anticyclonic circulation or PJ pattern here. So, but it is opposite. In August, there is a strong PJ-like pattern or anticyclonic circulation, and therefore your rainfall pattern is not well predicted by the model, because you need to predict these modes correctly in order to predict the monsoon well. So in 2021, in addition to PJ and the weak La Nina conditions, we have one more pattern. It is a Atlantic Nino climate model. Though this Atlantic Nino in 2021 has a minimal impact onto the monsoon, and we have a strong impact from the mid latitudes. In August 2021, we have low rainfall over India, and it is strongly associated with southward displacement of Asian jet. And in September, high rainfall is associated with northward displacement of Asian jet, and there is a strong anticyclonic circulation. When you have this strong anticyclonic circulation on the easterlies in the southern flank of this anticyclone can strengthen the shear, and that can cause a baroplanic instability, and then you have a vertical motion, and it can cause high rainfall over this region. Again, the impact of La Nina is minimal over here, and even the Atlantic Nino is minimal. So impact of mid-latitude circulation changes seems to be very important in altering the subseasonal rainfall. That is, again, SRP pattern is dominating over this region. And this is just schematic illustrating the mechanisms which I have explained. And now the models showed kind of very limited skill in capturing the subseasonal variability in the rainfall, and even CFS2 also have a problems because the circulation over the mid latitudes and Western North Pacific and associated rainfall is not well predicted in these models. And 2022 is very interesting because it is this year is last year of the La Nina. It is a triple La Nina year, because the La Nina started in 2020 and then continued to 21, and then strong La Nina is seen in 2022 summer. So apart from La Nina, we have Indian Ocean dipole, negative Indian Ocean dipole. So there are two modes again operating, and which is important for the monsoon variability is need to be examined. So when you examine that, you can see that there is a dipole-like pattern here. So low rainfall over southern China and eastern parts of India, and then western parts of India has a high rainfall. The model, when forced with the only tropical SSTs, it could simulate the dipole-like pattern with some differences with the observations. Now, which mode is important in order to simulate this rainfall is important. So when you take out the influence of tropical Indian Ocean in the model by prescribing climatological SST, what you see, the rainfall is increasing even South China and entire India, indicating that IOD has certain impact on the low rainfall over the eastern parts of India and southern China. So when you see the difference between control run and the experiment, what you will see close to the observations, indicating that though there are two modes, they can have an influence separately onto the monsoon and regional patterns. And this is how the schematic is explaining. You have strong Hadley cell and causing low rainfall over that region, and the La Nina can contribute high rainfall over the northwest India. Apart from this, the Azure high seems to be strong during 2022, and it actually triggers the mid-latitude Rossby waves, and it influences the monsoon. And recently we found that the Tibetan amplification seems to be also playing an important role. So there are again multiple modes operating onto the particular season of the monsoon, and they are changing the seasonal patterns of the monsoon. And 2023 is different from other three monsoons, which we have discussed, because 2023 was a strong El Nino year. And when you have strong El Nino, generally we have a kind of below normal rainfall over India. But in 2023, it was a normal monsoon year, and only August has experienced a low rainfall. So what is the factors that are responsible for this particular deficit monsoon is that there is a westward extension of the El Nino related SST anomalies, and there is a strong cyclonic circulation over this northwestern Pacific. When you have this strong cyclonic circulation, you have a deep connection over that region, and the zonal branch can have a subsidence over the India, and it suppresses the rainfall over this region. Not only this, there is an impact of mid-latitude circulation, because the underneath warming associated with El Nino causes strengthening of westerly jet and wavy pattern in June itself in 2023. When it comes to July, this wavy pattern is propagating towards the Atlantic, and then by August, you can see this wavy pattern is reached to the Asian region, and this particular cyclonic circulation like pattern is again supporting the upper level divergence here. So upper level convergence. So because of strong divergence here, you have an upper level convergence, and this is again supported by mid latitude circulation. So here, instead of mid latitude circulation, tropical anomaly seems to be a dominant. When tropical modes are very dominant, the impact of mid latitudes is a kind of minimal. When there is a strong strong impact of mid latitude waves, and you have a very weak modes in the tropics, mid latitudes are going to be dominant. And then one particular event can change your entire outlook of the monthly rainfall, or even monthly rainfall, or first half of the rainfall, first half of the monsoon, or second half of the monsoon. Now in 2024, there was a strong rainfall event happened between 21 to 30th 2024. So you can see that heavy rainfall is happened. Actually, the 2020 till 20 August, the monsoon seems to be very weak in the August, but from 21 to 30th, heavy rainfall contributed to the monthly monsoon rainfall. And then this particular event is also linked to the large scale SST patterns. When you look at the SST patterns of August, there is a warm SST over the kind of central Atlantic, and this warm SST could cause strong convection over that region, and because of the strength of the convection over that region, eddy growth rate has increased in the middle of the August. This eddy growth rate is very important. So this Rossby responds to enhanced baroclinic instability. This eddy growth represents the baroclinic instability. So showing a strong energy propagation from here, Atlantic, to the Eurasian region and then Asian region. So once the baroclinic instability is very high, and then enhance the westerly jet over that Atlantic region, and there is a strong jet, and then the Ural blocking caused like omega shape of the Rossby wave, and that actually moves towards the Asia, and there is a strong jet streak over this region. So when you have a strong jet streak over this region, and north of it means the entrance of this jet streak will have a strong cyclonic circulation in the left side, and that causes an indirect northward transport. This is actually, this jet is not a very clear geostrophic. It is like a geostrophic wind. So a strong geostrophic wind causes a kind of northward transport over this region. Because of that, you would see that there is a kind of the air depletion over that region, and then it can cause a upward motion. So because of the increasing strength of this westerly jet over this region, and the recent years, the jet streaks seems to be more frequent in the changing climate, and this has strong impact on the monsoon. So because of these mechanisms, we have a kind of heavy rainfall over the northwest India, and it is causing a low rainfall over the northeast India. So basically, large-scale climate teleconnections significantly influence not only the seasonal mean monsoon rainfall, but also subseasonal rainfall and regional distribution. In recent years, combined effect of multiple multi-teleconnections or multiple teleconnections appears to have contributed shifts in the regional patterns of ISM rainfall, and understanding how these multi-teleconnections might evolve in future is a critical area of investigation. Thank you.
Thank you, Dr. Dusty Chaudhary, for your insightful talk. Now moving to the final talk of this session, may I now kindly invite Dr. Nancio Mulukesh to deliver his talk on Arctic to Tropics two-way teleconnections. He'll be joining us online. Dr. Nancio Mulukesh is a distinguished scientist at National Center for Polar and Ocean Research. His research has significantly contributed to our understanding of Southern Ocean sea ice processes on interannual timescales as well as science of tropical polar teleconnections. In recognition of his outstanding contributions to the field of polar science and technology, Dr. Mulukesh has been honored by the Certificate of Merit by Government of India. Sir, you can please share your PPT.
Yeah, thank you. Am I audible?
Yes, you are audible.
Is this shared? My screen is shared?
Yeah, it is visible now. Please go ahead. Sir, please do full screen.
Sorry?
Full screen mode.
Yeah. Yeah, is it, you can see it?
Yes, now it's fine.
Yeah, thanks for this invitation and to Director IATM, Dr. Suryan Rao, as well as Dr. Gnanashilan for inviting me to this interesting one-day workshop. Almost all of you are the tropical meteorologists, but I'm not a meteorologist by training, not by practice as well. But what we do here is to understand the polar regions and how it is linked to the tropics. So these are some of these work that I presented, a part of our work that we have done here. And see, one of the interesting, so the screen is moving.
No.
Can you share?
Okay. Yeah. Now it's good.
One of the very interesting, not by the New York Times way back when the first Indian Antarctic expedition was launched, was this. So it says that according to Indian news dispatches, the expedition was particularly interested in studying the effect of Antarctic and surroundings on monsoons in India. So the understanding the teleconnections from a polar perspective was on the minds of the people who has framed the polar studies in India in the long time back itself. So we are still no different from that. Actually, we have continued this study and we have expanded our studies not only to Antarctica, but to the Arctic and Arctic as well, and into the surrounding oceans like Southern Ocean and to the Himalayas as well. So that's where we stand in terms of the polar research now in the country. And see, there are certain things that that come to our mind when we think about the polar regions. One is that the ecosystem services that is carried out by the polar regions. If you see that, this is an interesting paper that appeared some time back, and the Arctic physical change, you can see the right side of the diagram, it has an indirect global impact where climate change feedbacks and teleconnections. And it leads to the extreme weather events and to global precipitation and the changes in the ocean circulation patterns. And this in turn, the study identifies that this in turn will lead to increasing threats to highly populated and large economic regions, and that includes India. So the understanding the polar regions and its impact has been at the forefront of our studies quite recently. And why the teleconnections change? Because as the polar regions form, the thermal gradient between the polar and low latitudes decreases, and the change in climate parameters like atmosphere ocean CAS and the feedbacks and the albedo in the polar regions also changes, which is having an impact on the radiation balance. And this changes will lead to the changes in ocean and atmospheric circulation patterns. And if you see the Arctic, this talk is particularly focused on the Arctic itself. And if you see the Arctic, one of the most interesting thing about the polar regions is the ocean surrounding it is covered by is the oceans surrounding it. In terms of for Arctic, it's the ocean itself. And if you see that the seasonal cycle of the sea ice in the Arctic, which almost close to more than 80% of the Arctic will be covered by sea ice during the time, and it oscillates to almost about 4 million square kilometers during summer. And this oscillation itself is so huge that it is almost 3 times the area of this of our country. So that much area of the ocean will be exposed during summer and will be closed for ice interactions during winter. So this is something quite remarkable. And you can see that in the recent times, the Arctic has been warming quite intensely. And in some locations of the Arctic, the warming is almost 7 times than the global rate of warming. So the global rate of warming. And this has quite far-reaching consequences in the Arctic itself. And you can see that the Arctic sea ice has declined over the past 4 decades or so. And this has removed almost more than almost about an area of ice is almost close to the area of this country from the Arctic, which means that the last 40 years or so, the an area of the size of India is exposed to the ocean atmospheric interactions within the Arctic, which will, of course, we can expect that this will lead to an altered ocean atmosphere circulation pattern and teleconnections. So even in the under low emission scenarios, in the future of the Arctic sea ice is concerned, even in the low emission scenarios, Arctic will be ice free soon. So this is what the studies are pointing to. So we have. So how will that change in the rest of the world? There are different types of impacts that we can find in terms of heat and water exchanges, ocean atmospheric circulation. There will be a lot of rivers that will be discharging into Arctic, which will change the stratification of the Arctic Ocean, and then it will have an impact on the global carbon cycle as well, which is again going to impact in many ways. Which will impact the globe in many ways. So this is a recent newspaper report that has published some time back, and it is saying that the North India is as cold as Southern Europe because of Arctic winds. How this happened is because of the wobbling of the strong jet stream, wobbling of the jet stream because of the weakened temperature gradient, and it intruded into the northern India, which create almost Arctic-like conditions. So the warming has reduced the thermal gradient, which made the jet stream to wobble. A similar kind of wobbling was also noticed recently in a paper by Mahendra et al. during summertime, and which has resulted in above normal rainfall during August. So these are the kind of things that we have been seeing in the observations when we study the impact of Arctic on tropics. And recently that we have also contributed to the understanding of Indian summer monsoon rainfall in August, in the summer monsoon rainfall and the extremes in the northwest of India, which the sea ice decline in the Barents and Karasul, whereas a location in the southeast of the Arctic, which is resulted in changes in the jet stream characteristics, and then which has impacted by the Rossby wave activity flux towards subtropical Asia, which will lead to intense extreme rainfall over the northwest of India. Similarly, we have also note that the Arabian cyclone characteristics have also been altered by the warm Arctic and cold continent pattern. This is a pattern that has been emerging in the Arctic, which is the characteristic of which is the Arctic Ocean is getting warmer, and at the same time, the northern part of the Europe is getting cold. It's called the warm Arctic and the cold continent pattern. And we have seen that the intensification of tropical cyclone over the Arabian Sea is partly driven by these teleconnections. Again, we have conducted this study with only the decline of decline of sea ice in the Barents and Karasin's model using Hadley Center models, which again suggests that an intense precipitation events can be observed in the northwest India during the summer monsoon season. So the Barents and Karasi could be an important location where the teleconnections can be managed from it and can have can reach as distant as the tropical countries like India. So this is the recent study that came from IATM itself, which shows that extreme events in the northern India is been associated with June, July, August displays concentration. The mechanism is very simple that has been found in most of the studies. It's the Rossby altered Rossby propagation pattern. This is depicted in the right hand side of right hand panel. So what we have essentially seen, okay, it is not only the winter, the summertime precipitation, but the wintertime activities also is wintertime atmospheric circulation is also modulated by the this particular study deals with the atmospheric circulation anomalies during positive phases of Arctic oscillation and negative phases of oscillation, which shows that very clear and clear difference between the radioactivity flux emanating from the Arctic into the tropics. We can see a very clear radioactivity that reaches during the positive phase of air, and we cannot. There is not so much of an activity which has taken a different altered path during the negative phases of the Arctic oscillation. So there have been there are many studies that is pointing towards the impact of the Arctic onto the tropical regions by means of with altered atmospheric circulation and changes by the Rossby wave activities, which in fact is due to the changes in the heat exchanges between the ocean and the atmosphere in the Arctic. So, but at the same time, you also note that the teleconnection is not only from the Arctic to the poles to the tropics, but you also note that the teleconnections can also be from the tropics to the pole as well. This is a study that we have conducted some time back, which says that during the MJO, which is active in the Western Pacific, can trigger those period of anomalies that can reach all the way up to the Arctic. In fact, we have noticed that our observational facilities in the Arctic have recorded extreme temperature and precipitation anomalies during the on the random time scales also. We have noted that this the ENSO and the Arctic, and in fact this is the B represents the second UAF mode of the sea level pressure anomalies in north of 40 degrees north, and that the time series of that is very well correlated with an inotary. And in fact, this in this particular event was actually an interaction of an MJO activity and the ENSO during 2015-16 winter. So, so what it suggests is that not only one particular process, but there is an interaction of multiple processes that we can find in the Arctic that is emanating from the tropic, which will be true for the pole to tropic teleconnections as well. And again, another study which states that we have the extreme rainfall events that has occurred in the northwest of India and Pakistan has triggered Rossby wave anomalies, and which traveled all the way up to the Arctic. And this is called a circumglobal wave train. So now it's becoming quite clear that the hemisphere, the northern hemisphere at least, is what you call is connected by means of this ocean and atmospheric circulation patterns. And this is a wonderful study that is some time back by the late Krishnamurthy, which says that the intense rainfall event on and northwest of India has triggered made the heat anomalies to reach all the way to the Canadian Arctic and causes the sea ice melt. So this is something very remarkable that we have been discussing about the sea ice melt and the intense summer monsoon rainfall. But at the same time, the monsoon itself is causing the sea ice melt. So this is what we call the two-way teleconnections, in fact. So this shows that the hemisphere is linked on what you call intraseasonal timescales to interannual timescales. But at the same time, so there is something that is quite different that is happening in the Arctic. It's actually a kind of a new low frequency variability that is developing in the surface temperature of the Arctic. So what does this mean? This means that we have been studying the current teleconnections pattern, but at the same time, the teleconnection pattern itself is going to change in the future. So this study shows that it is going to be stabilized after some time, but right now there will be some sort of uncertainties that are going to that we are going to find in the teleconnection patterns because of this emergence of new low frequency variability in the surface temperature of the Arctic. So then again, that we have there are problems in particularly when we deal with the models and rely on understanding the teleconnection. This particular study shows that the number of low pressure systems during the monsoon season is much reduced when the sea ice is removed from both the poles. This particular model does not show so much of sensitivity to the Arctic sea ice, but when the Arctic sea ice is declined in both the poles, it shows that there is a reduction in the low pressure system. In the first talk that Surendra was mentioning about the systems that is developing in this location and how its contribution to the monsoon rainfall. So right now, though we see that certain observational studies which target particular events, such as the link of the polar sea ice or polar influence on the monsoon rainfall, or sea ice on the monsoon rainfall, the Arctic sea ice on the monsoon rainfall. Some of the models are unable to capture those kind of variabilities. And most of the times that we rely on the simulations to understand the future variability of sea ice and its impact on the monsoons. But the sea ice, the smaller simulation itself has a large model variability among the models. And most of the models are simulate too much growth in winter as well as too much melt during the summertime, which is not consistent with observations. And there again, that's a similar which suggests that the Arctic sea ice CMIP6 models, and these are the red and purple, the red and pink curves indicates the observations, and the black line indicates the CMIP model, and the gray ones are actually the individual model ensembles, which says that the reason here is none of the model is unable to capture the interannual and what you call the tendencies in that has been found in the summertime sea ice anomalies in Arctic as well as in Antarctica. So this suggests that there are more work need to be done in representing the sea ice and simulating the sea ice in the models to understand its teleconnections with the tropical regions, particularly the monsoons. So, in short, what it suggests is that there are oscillating trends which can emanate from the tropics as well as from the poles, are the main mechanisms of teleconnections and the precipitation that is happening in the tropics, and the polar regions are rapidly changing, and the proper representation of components will help to understand not only the precipitation but kind of interconnected global system and its response to the changing climate. And we can achieve this by having continuous and long-term observations in the polar regions. And that is my final take on it. Like this, the Arctic and the tropics is interconnected, at least on hemispheric and hemispheric scales climatically. So I think I'll stop there. Thank you for the opportunity to deliver this talk here.
Thank you, Dr. Mulkesh, for your insightful talk on Arctic to Tropics Teleconnections. With this, we conclude the morning session of our workshop. I extend my heartfelt thanks to all the esteemed speakers for their insightful and thought-provoking talks, which have truly enriched our understanding. Now it is an announcement for all our online participants. Our afternoon session will start at sharp 2:20 p.m. I request all the online participants to please rejoin at 2:20 p.m. I now request all the dignitaries and participants present at IATM to kindly proceed for lunch served at IATM guest house. Very interesting. Have more. Yes.
Section from
Yes.
right. I written only have to tell that. Was at that time, yes. Tell me, just ask me. मतलब IMDb कौन सा पोस्ट है? SRF, MRF. हो जाएगा इस बार. आपका काय आपको भी हाँ भी गया है ऑलमोस्ट, लेकिन पुणे यूनिवर्सिटी से हुआ है रजिस्ट्रेशन, तो के बाद कर सकते हो, कर सकते हैं इसे इसी जुलाई के बाद कर सकते हैं. पुणे यूनिवर्सिटी में ही है, रात महाराष्ट्र है आप, लेकिन सिनॉप्सिस के साथ ही दे सकते हैं क्या थीसिस में? सिनॉप्सिस होने के बाद ड्राफ्ट थीसिस करके सबमिट करना होता है. थीसिस वो इंटरनली जो रिसर्च होगा ना, वो लोग देखेंगे, कुछ है तो बताएंगे, आने के बाद पूरा फाइनल करके थीसिस सबमिट करना. उसके बाद टाइम ड्यू रहती है. एक महीने अपने आप कभी भी 3 महीने के 1 महीने मैक्सिमम तो थोड़ा स्मूथ है, बट हम रजिस्ट्रेशन करने के बाद वहाँ पर भी हाँ वो तो रूम भी है लेकिन अभी अगर जैसे स्टूडेंट्स के लिए ACS या वो कर रहे हैं हम जो लिस्ट हमने जो फेस किया वो लोग देख रहे हैं. बेटा क्या है क्या कुछ नहीं पता बात होता है.
Good afternoon, Dr. Yu. Good afternoon.
Hi.
How
Good
are you?
afternoon.
Yeah, yes. I'm Janashil, yes.
It's hard to see. It's too distant.
They can. I'm going to see. Okay.
Are you Justin?
Hi, Justy. It's very long time no see.
After 14 years.
14 years.
Yeah.
Oh.
Yeah.
Since you left our PLC.
Yeah.
Okay.
Nice. It is good to see you.
Good to see you. So, can I try screen sharing?
Yeah, please.
It's my first time to do presentation on Teams.
Yeah, we can see.
So does it?
Yeah, we can see that.
Will it work? Okay.
Yeah, it's working. Yeah. It will work.
Hi, Annalisa.
Yeah. Good morning, Annalisa. Yeah, she probably got up very early, midnight. Enjoy. We'll start in 2 minutes. So we have 2 more minutes.
A very warm welcome to all of you for our afternoon session. We'll be starting our next session. It is now my pleasure to invite Dr. Yu Kosaka to deliver her talk on skillful predictions of the Asian summer monsoon 1 year ahead. Dr. Yu Kosaka is currently serving as Associate Professor at the Research Center for Advanced Science and Technology, University of Tokyo, Japan. In recognition of her outstanding scientific contribution, she has been honored with the Young Scientist Prize under the Commendation for Science and Technology by the Ministry of Education, Culture, Sports, Science and Technology, Government of Japan. Dr. Yu Kosaka, please go ahead with your talk.
Thank you very much. Can you hear me?
Yes,
can you hear me?
we can.
Okay. Thank you very much. It's a pleasure to have this opportunity to give my presentation at this workshop. So this is not like a review, but I would like to focus on a specific study done by my colleague, Dr. Yuhei Takaya of Meteorological Research Institute of Japan Meteorological Agency. But I hope this study matches the focus of this workshop. So this this is not actually a very new study. It has been already published 4 years ago. So if you're interested, please take a look. This is published on Nature Communications. So the Asian summer monsoon consists of a few regional components, and there is a co-variation of those components of regional monsoons. And the left figure show regression anomalies associated with the Western North Pacific summer monsoon. So this is a sign-flipped anomalies associated with the Western North Pacific summer monsoon index, which represents the lower tropospheric meridional difference of surface zonal 850 hectopascal zonal wind. So this anomaly is this map is linked to the anomalies in the Western North Pacific region with the anomalous anticyclone with suppressed precipitation over the Western North Pacific, but the signature extends westward to South Asia. And also it is linked to the East Asian, mid-latitude East Asian climate through the teleconnection called the Pacific Japan pattern. So the Western North Pacific summer monsoon prediction is important to the world's most densely populated region. But formally, its seasonal prediction was difficult because of the dominance of the atmospheric influence on local SST in the tropical Western North Pacific. So the right figure here shows interannual pointwise correlation of precipitation and SST in JJA season. And in the tropical Western North Pacific, the correlation is weakly negative, despite the high climatological SST exceeding 29 degrees C. So the negative correlation suggests that the SST is not a driver of precipitation, but instead SST is a response to precipitation. But later, it has been recognized that the Western North Pacific summer monsoon variability is driven not by local SST anomalies, but instead remotely by the Indian Ocean basin-wide SST anomalies. So a study by Shea et al. 2016, which Dr. Chaudhary also introduced, identified an interbasin air-sea coupled mode, which we call the IPOC mode, Indo-Western Pacific Ocean Capacitor mode. And here, the atmospheric equatorial warm Kelvin waves that penetrate into the Western Pacific, and Western North Pacific summer monsoon anomalies, and the westward phase propagation of atmospheric Rossby waves are linked with Indian Ocean basin-wide SST. And this interbasin coupling forms the IPOC mode. So the seasonal prediction of IPOC mode can be a key to the seasonal prediction of the Asian summer monsoon. And importantly, whereas the IPOC mode is an intrinsic air-sea coupled mode, ENSO is an important driver of the IPOC mode. And this triggering of the IPOC mode is not concurrent, but instead it occurs in ENSO decaying season. So indeed, the decaying ENSO is a major driver of the IPOC mode. So this can enable the seasonal prediction of the Asian monsoon. So here, I would like to note that the ENSO development is predictable after the so-called spring prediction barrier. So together with the lagged ENSO-IPOC relationship and this ENSO prediction, it suggests that the IPOC mode may be predictable in the boreal spring season, after the spring prediction barrier of ENSO, for the subsequent year of summer Asian summer monsoon. So the ENSO-IPOC relay may enable prediction of Asian summer monsoon in the spring of the preceding year. So this is our working hypothesis, and we tackle this challenge by analyzing an ensemble coupled model hindcast simulations. So we used JMA-MRI coupled prediction system version 2, which was an operational model of seasonal prediction at the Japan Meteorological Agency. Now, currently, it is replaced by version 3 of the model, but it was operative until a few years ago. So Dr. Takaya conducted an ensemble hindcast initialized in April of every year from 1979 to 2016, and which extends to the second boreal summer. So it's initialized in April and predicted first boreal summer, and then to the further into the second boreal summer season. And this prediction consists of 52 ensemble members, and we mainly I mainly show today's talk the second summer prediction, except for last part where I would like to discuss the tropical cyclone activity prediction. Okay, so this is a prediction. This figure summarizes the prediction scale for the second summer of the key Asian summer monsoon indices. And red is the observations, and blue is the second summer prediction. Actually, the magnitude is adjusted to match the observations for easier comparison. So Western non-specific summer monsoon index is correlated with between observations and prediction at the correlation is 0.5. And even after detrending, the correlation is again 0.5, which is 99% significant. And we also compared some key indices like Nino 3.4, whose correlation is actually lower than this one, and also the Indian Ocean Basin SSD, for which we found the correlation to be 0.7. And after linear detrending, the correlation is still 0.52. Also, the Western North Pacific rainfall, which it's very highly correlated with the WNP summer monsoon index, also shows some significant scale. And also, we picked up two regional indices like Ganges River Delta rainfall. The correlation is slightly less than 0.5, and Indochina Peninsula SAT, the correlation is even higher. Even after linear detrending, the correlation is 0.65. So this is the map of observation and the prediction correlation. I mean, point-wise correlation between observations and predictions for SST and land surface air temperature. This is 850 zonal wind, and this is precipitation. So we see broad areas of significant correlation in the tropics with a correlation of 0.3 to 0.5. And the structure is roughly consistent with the potential predictability, which has been estimated through a perfect model approach of the same model. So also we found that we confirm that the structure of high correlation is consistent with the structure of the IPOC mode. So this is the observation-based anomaly structure of the IPOC mode, which is here represented as a regression onto the Western North Pacific summer monsoon index. So we see air temperature signature over here, which is represented over here, and also the rainfall reduction and increase. This is found here and also extends to here, and zonal wind scale extends from the tropical Western North Pacific into India, which is highlighted here. So this results suggest that the skillful climate prediction is dominated by the contribution from the successful IPOC prediction. Also, we examined the ensemble size dependence. So this is like Dunstone et al. Plot. X-axis is ensemble size, and the y-axis is correlation of the WNP summer monsoon index, and first summer and for second summer. So we found as the ensemble size increases, of course, the scale increases. And to obtain a correlation scale of 99% confidence, we need roughly 20 members or more of the ensemble members. And there is still small but not negligible margin for further improvement with further increase in the ensemble size. And also, we found that there is no apparent signal-to-noise paradox. The potential predictability estimated through a perfect model approach is generally higher than the actual model scale, which doesn't suggest the so-called signal-to-noise paradox. And the correlation pattern is also consistent with the No, sorry. So this one. So then we further examine the origin of this successful prediction to see if the ENSO-IPOC linkage is indeed the major origin. So the left figure shows a correlation scale as a function of lead time. So 1 means first summer, and here is the second summer. And we see, as expected, ENSO prediction score gradually decreases with the lead time. And it keeps, the correlation keeps above 0.7 until the boreal winter season, then decreases, especially during the spring prediction barrier. And the second spring, it rapidly drops and becomes, the correlation becomes insignificant. But in contrast, the Indian Ocean Basin SST prediction score doesn't fall so quickly. So it actually decreases first, but then recovers. And this high correlation is maintained until the second summer. So even in the second summer, the correlation is something like 0.7. This is consistent with a typical timescale, time evolution, seasonality of ENSO and its impact on the Indian Ocean basin mode. So this is the autocorrelation of Nino 3.4 and correlation with Indian Ocean Basin SST, and the x-axis is a seasonal lag. So this is ENSO peak season, and ENSO develops in the boreal summer to fall season and peaks in boreal winter and rapidly decays. But its impact on Indian Ocean Basin grows and maintains its signature until the second summer. So this delayed lagged influence of ENSO on Indian Ocean Basin mode enables this high predictability until the second summer, and then drives the IPOC mode, which enables us the prediction. Also, this is a composite of post-El Nino summer from observations and from prediction system. So the composite is taken for 6 major El Nino events. So we see the structure of the simulated signature is overall consistent with Indian Ocean warming and the atmospheric warm Kelvin's wave signal in the tropospheric temperature, and a weak Western North Pacific summer monsoon, which extends westward. And we also found that excluding these 6 events from the statistics, then the correlation scale of the WNP summer monsoon index falls from 0.5 to 0.26, which suggests that indeed ENSO is the major origin of this prediction scale, at least in this system. And also we are interested in the Western North Pacific tropical cyclone activity. And this is, we also compare the first summer and second summer. So this is tropical cyclone density over the Western North Pacific in the boreal summer season, JJA season only. Now observations and our prediction has a significant correlation, at least for the first summer, with a correlation of 0.67. And even for the second summer, there is some scale, not very high, but the scale is 0.39, which still exceeds 95% confidence level. And this is contributed to by 2 processes. One is a concurrent El Nino, and the other is IPOC, decaying ENSO signature. So the concurrent El Nino leads to a southeastward shift of TC genesis in the Western North Pacific, which leads to longer tropical cyclone track. So the El Nino tends to have a higher concurrent tropical cyclone density in the tropical Western North Pacific region. And also positive IPOC accompanied by warmer Indian Ocean tends to accompany a decrease in TC genesis, which leads to a reduction of tropical cyclone density in the Western North Pacific. And both of these signature contributes to the first summer. But the second summer, the concurrent El Nino signature doesn't contribute to this one. So it only works in the from the Indian Ocean influence. So in the summary, a large ensemble coupled prediction initialized in April can predict Asian climate anomalies in the second summer to some extent. And Western North-Pacific TC activities were predicted for the first summer and moderately for the second summer. So the ENSO IPOC relay brings the predictability well above the noise level. So the key is the initialization after ENSO's spring prediction barrier and a large ensemble of more than 20 members. And also important thing is the successful prediction of not only the development, but also the subsequent decay of ENSO. ENSO development, but the decay must be predicted. And then followed by the IPOC development. And also to have a skill of a local climate, we need a realistic simulation of regional climate anomalies associated with the IPOC mode. So our mechanism understanding suggested the predictability, and this predictability is indeed validated by the prediction model. Okay, I stop here. Thank you very much.
Thank you. Wonderful talk. And if you look at the second year prediction for air temperature over India, the skill is much better than over East Asia, over Indian subcontinent.
The skill is
previous one.
This one?
After this. The air temperature.
Air temperature.
The next.
Not very much. Better than East Asia, but the structure is not extremely good.
And not this one.
Not this one.
One more. After.
No, not this one. So
forward. Yeah, here, this one.
This one.
This one.
This is a ENSO signature actually.
Yeah.
So this one suggests some overestimation of ENSO signature compared to reality.
Okay. Is this the model bias?
Yeah, potentially.
Oh, okay. Yeah, because the model responds to okay. Yeah, that's why you don't get a good rainfall prediction over the Indian region.
And also the model has a too persistent ENSO. So in observations, we already ENSO signature has disappeared, but in this model, we still have the ENSO signature. So there is some bias in ENSO representation also.
Okay. Thank you.
Can I ask a small?
Yeah. Please go ahead.
Kosaka-san.
Yeah.
Good talk.
Thank you.
I just wanted to give a small feedback. You talked about ENSOs and typhoons. There is a positive. What you are indicating is a positive correlation, or?
Concurrent El Nino leads to increase in TC density because it shifts the genesis location of the
I got your point. I just wanted to give you some feedback. There was we had a paper in 2011, and Chen and Tam in 2010, and Webster had one paper. Depends on the type of El Nino. If you have a Modoki, it increases. If it's a canonical El Nino, the numbers decrease. There is a totally. I mean, you must have used Nino 3.4 or something, so it captures both. So if you take these two separately, you composite, the signals change. Just sort of feedback to you. That's all.
Okay, thank you very much.
Thank you, Dr. Yu Kosaka, for the insightful talk. Now let's move forward. May I now kindly invite Dr. Annalisa Cecchi to deliver her talk on the topic Global Climate Models for Monsoon Predictability and Predictions. She'll be joining us online. Dr. Annalisa Cecchi is a senior scientist at the National Research Council, Institute of Atmospheric Sciences and Climate, Bologna, Italy. She is an expert in tropical climate variability, particularly in Indo-Pacific region, with a special focus on Asian summer monsoon and its predictability. Dr. Chetty has significantly contributed to C20C climate framework aimed at exploring the connection between the Asian summer monsoon and ENSO. She has served as a lead author for the IPCC 6 Assessment AR6 working group. Currently, she co-chairs the WCRP Lighthouse activity on the Global Precipitation Experiment and serves on the Scientific Advisory Board of the International Foundation for Big Data and Artificial Intelligence for Human Development. Dr. Chetty, you may please start your presentation. You can see the presentation, right? You are not audible. Can you please mute? Unmute again.
Okay.
Yeah, no, still not audible. Maybe some mic setting, some problem.
Yeah. Now, yes. Now,
no, still not working.
Previously it was working, but now.
Settings. Can you please go to settings and select microphone? Microphone and then click on again speakerphone or something. Still not audible.
Yeah, now.
Now can you please speak?
In between.
I think it is breaking.
Do you hear me?
Yeah. Now it is fine. Yes.
Okay. Okay, thank you.
Yeah. We are sharing your PPT from our side.
Yes, thank you. Thank you very much for sharing.
Yes.
Yes. Okay, so thank you for this opportunity to present this these slides that I collected thinking of, you can go to the next slide. So thinking of few aspects that are related with how global climate models can represent monsoon and how this is connected with the predictability and prediction. And this is also aligned with some of the research that I did and that I have done and that I'm still doing. Next slide, please. So I start with this result from the IPCC, just thinking of the opportunity that the multimodal intercomparison gives in terms of trying to understand what is the improvements that we have in the models. This is, for example, a representation of the global monsoon domain and intensity. So looking at the figure on the top, we see the spatial pattern of the global monsoon precipitation and the global monsoon winds, together with the red contours that align what is defined as the global monsoon. And we have on the left the observation and on the right the models. Just looking at these differences, we can see that there are realistic representation of the monsoon domain and of the monsoon intensity, and thinking of what happened in the past and looking also at the figure on the top, on the bottom, we see that we can consider that there has been improvement in the representation of the monsoon in the different evolution of the couple models and of that intercomparison. And we see also some aspect of the variability. Let's go to the next one. So one important aspect that we can learn from this couple model experiment, where we have also the chance to force with different type of forcing, we can sort of describe the attribution of monsoon precipitation changes. So if we consider the figure on the top that shows the June, July, August precipitation trend, this is taken from CMIP 5 model results. So it's a bit outdated, but still it gives the key information that I want to deliver. That is that the changes, the trend in the end of the last century was mostly driven by changes associated with the anthropogenic areas, so that have a different effect with respect to what the greenhouse gases has on the precipitation. And this is particularly true for the Asian monsoon. Then if we go and look at the figure in the bottom, we have the different monsoon regions as they were defined in the last IPCC report. And here we see as well that comparing the different simulation having all the forcing, only the natural or only the greenhouse gases or only the aerosol, we clearly see in the South Asian monsoon and East Asian monsoon that there is this counteracting influence that is then translated and visible also in the global monsoon average. Next, please. Okay, then if we consider that we have a realistic representation of monsoon in the historical period, then we want to see what happens in the projection. So again, thinking of the global and regional monsoon domain, we have in the figure in the top the global land monsoon precipitation index, and we see that moving forward toward the future climate projection as represented in the SSP scenarios, we see increase in global land monsoon precipitation, and at the same time we see a decrease in the circulation index. That is a quite known aspect of how the circulation works over the monsoon region. Again, this change is mostly dominated by what happens in the Asian monsoon, because when we look at the different regional monsoons that we also have seen in the slide before, we clearly see that the global monsoon, that is the black color on the left, has this continuous increase in the near term, mid-term, and long term. And the same is true for the East Asian monsoon, for the South Asian monsoon, and also for the Australian and the maritime continent monsoon. But that is not true for the North American monsoon or the South American monsoon, where it is difficult to see if there is a positive or negative change in the precipitation. Next slide, please. Okay, and this comes to this type of analysis and understanding that is associated with what is the hydrological sensitivity. And here we have again the 4 scenarios that was considered before, and we have these graphs that show the stepwise differences in terms of 20 years average with respect to the reference period, that is 1985-2014. And we see the global monsoon on the left, and then on the right we see the different monsoon. What it is clear is that in the South Asian monsoon and East Asian monsoon, despite the fact that there is a tendency toward having increased precipitation with increased global warming levels, still there is a non-linearities in terms of the scenarios that we consider. And for example, the red line, that is the scenario that is the 3.70, has a different behavior. So there is a non-linearity that is mostly likely associated with how the anthropogenic aerosols are represented in that specific scenario. And again, the behavior of the other monsoon is somehow tricky. And in most of the cases, like in the North American monsoon and South American monsoon, we have difficulties in having a clear signal because of the model spread. Next slide, please. This comes back to a quite old analysis that I did a long time ago, where I tried to decompose the precipitation changes. At that time, there were a sensitivity experiment to increase CO2 forcing, but still, we were able to diversify the different monsoon in terms of the mechanism at work. So thinking that the moisture term was mostly dominating the increase in precipitation with respect to the other term, and classifying the monsoon in the sort of classical monsoon, like the Indian summer monsoon, the East Asian monsoon, and the other monsoon that were probably most likely dominated by the dynamics rather than the thermodynamics. Now we have more information, thinking that there are also other factors at play, like the aerosol and that. And more recently, something similar has been done considering the global land monsoon, and trying to diversify the northern hemisphere with respect to the southern hemisphere. And again, there is largest uncertainty in the subdomain, in the submonsoon precipitation projection with respect to the global monsoon. And that's because the global monsoon is mostly dominated by what happens over Asia and East Asia. Next slide, please. Other features that needs to be analyzed, and something has been done in the past, in the characteristics of the monsoon rainy season in terms of duration, onset, and retreat. This is a couple of works that reflects onset, retreat, and duration for the East Asian monsoon in the bottom, and for the different monsoon over Asia. And in the top, there are all the other monsoon, including the North American, etc. And you can see that there are some diversity with respect to what happens to the different regions and to the different scenarios. But what is most striking is that there is still, again, a spread within the model. So there is uncertainty associated with how the models represent these features. Next slide, please. Okay, one important aspect that could be think of as what changes during this evolution of the monsoon. One characteristic that is keeping changing is the horizontal resolution. And so easy questions or a natural question is, what is the effect of the horizontal resolution for the simulation of monsoons? So we see here that from the 90s toward nowadays, we have gone through quite a different shape of the horizontal resolution. Next slide, please. And this is 3 examples. So one study that was very, very dated back in time, that was one of my first studies about the monsoon, where I concluded that the main improvement due to an high resolution models are associated to regional aspects for the precipitation, Western Ghats, for example. And in 2019, something similar has been done for the NCAR CAM5 simulation. And here again, the conclusion was that the most likely improvement was associated to the regional characteristics. More recently, using the high-res MIP simulation, these studies published in Climate Dynamics have shown that, in fact, high-resolution model can have better simulation and better characteristics. For example, in this characteristics of the monsoon, like the onset, the withdrawal, and the duration, and also in how the change per decade is considered in the present and then can be reliable for the future. Next slide, please. Of course, increasing the resolution can provide improvements in the extremes across the different monsoon regions, and also can help in better representing the monsoon law that could be very, very critical for extreme rainfall events. Next slide, please. Okay, now a few slides about the internal variability and teleconnection. Here it is something that I did also some years ago. In the top, there is a tentative idea of thinking of what could be the potential predictability that was discussed also this morning, and thinking of this were an AMIP type simulation. So what could have been the influence of specific characteristic of the monsoon? And we see that the potential predictability is large when the spread among the model is small. But here there are some yellow beans that are these cases when the potential predictability is high, but the most interesting one corresponds to very high El Niño that mostly drive this predictability. Similarly, if we think of the AMIP type simulation and we think of the kind of SST that is needed to have Rossby wave teleconnection and then an influence on the monsoon, we can also have false information, because we can have the correct distribution, or we can have a distribution of the SST in the Pacific that could be enough in an AMIP type configuration to trigger a monsoon variability associated with ENSO, or we can have exactly the reverse if the SST is not exactly in the shape that is enough to trigger the teleconnection. Next slide, please. Here again, in terms of teleconnection, and someone Bearason this morning discussed more deeply about this. So this is idea on how the Indian Ocean dipole influenced the Indian summer monsoon and how this relationship is influenced by ENSO. This is too schematic of a direct influence and also a consequences of processes that are associated with what is called the biennial oscillation. But in any case, what is mainly important is the complexities of the different processes that are in place and how this change in time, as we have seen this morning. Next slide, please. Okay, this was a check of a relationship between the Indian Ocean dipole and how it progressed in future projection and how it was related with SST and precipitation. And this was just in CMIP6 simulation, where we see that there is a tendency toward high OD with larger amplitude, and in how the projection works in terms of how this is teleconnected with what happens in terms of precipitation and SST over the Indo-Pacific region. Next slide, please. Another type of teleconnection that I tried to focus on was the link that the influence that the Indian monsoon may have on what is called the monsoon desert mechanism. So what happens in the Euro-Mediterranean region in summer. On the left, the scatter plot that relies the relationship, that try to relate what happens in terms of omega at 500 pascals, so in terms of subsidence over the Mediterranean region, and the moisture, the latent heat, the heat that is produced by the monsoon precipitation. And in the maps, there are the composite of strong monsoon years and how this relates with the precipitation and subsidence. We have the observation in the top of the target analysis that have quite few number of events, unfortunately. And we have some models that, among the models that were the most able to represent that teleconnection, we tried to see what was happening there in terms of composite. And there is an indication that there is a signal, but it's really hard to have a very clear and strong signature. Next slide, please. And this is the last, like a flavor of prediction. This was a study that we did many years ago now, but it was on the subseasonal prediction. And the point was two ways. Was thinking of what could be the metrics that we can use to detect in the summer monsoon onset. And we evidence how the easiest way to have useful information from the model is to look at dynamical indexes. But also we had some improvement in the scale and forecasting earlier than normal ESM onset with respect to what are the late onset. And it's not shown here, but the reason was effectively in the propagation of of moisture and of winds from the Indian Ocean toward the Indian subcontinent, and it was associated with a good representation of the initial condition in the models. So I'm concluding here. Next slide, please. So I provided a flavor of different aspects that are important in terms of the representation of monsoon in the models, thinking not only to the Asian monsoon, but with a broader perspective on the global monsoon and also all the other regional monsoon. And we can say that there has been progresses in the performance of state-of-the-art GCM in representing the monsoon basic feature, but still there is a lot of work to do. And the main reason is that because of the complexity and all the interactions that we have in the models. We are having important information in terms of attribution, either for past changes and also useful for thinking of what are the projection of the model, but still we have model spread specifically for the monsoon region where the dynamics or there are more nonlinearities compared to the other the Asian monsoon region. The horizontal resolution could be a key information that we probably need to have as high as possible, but still it's not enough. It's not the alone solution to have a better representation of monsoon. And of course, all what is related with the teleconnection and the potential for the predictability that comes from the teleconnection has to rely on the processes and on the dynamics that we have in the model. So that is a room, there is room for improvement and for better research and more research. So I stop here so that we can have hopefully some interesting discussion afterwards. Thank you for your attention.
If you see your high resolution model prediction, the improvement is mainly coming from the ability to represent the extremes, or is there anything more the high resolution models can? The improvement is coming from that, or something more?
Sorry, can you repeat? Because
you have shown that extremes are represented better in the high resolution model.
Yes. Yes, that there are.
Apart from the extremes, are there anything contributed to the improvement in the mean rainfall?
So there are improvements that are all the improvements that are related with how we can better represent some regional precipitation pattern, because as we have seen also this morning, there are a lot of heterogeneity in how the precipitation varies and is is characterized over the Indian, or even only over the Indian continent. So this can probably help. But it's not the only solution. So that were just examples that were saying that in the course of the years, we are going toward higher and higher resolution, hoping that this could solve many issues. But we know that that's not the unique solution, that we absolutely need to work on the processes and on the dynamics to have something more in terms of mean features and variability.
Thank you. Thank you.
Thank you, Dr. Annalisa. With this, we now conclude the afternoon technical session. On behalf of organizing committee, I extend my heartfelt thanks to both the speakers for their insightful talks. I now request Dr. Jasti Chaudhary to kindly take over and initiate the proceedings of the panel discussion.
Good afternoon to all. So we have witnessed a fantastic two sections with enlightening talks. And now I would like to thank everyone for joining the panel discussion. So I will be moderating the panel discussion on monsoon variability, prediction, and predictability. So today, panel discussion will explore challenges on monsoon variability, prediction, and predictability by looking at recent developments and opportunities from multiple expert perspectives. So, to lead this discussion, we are privileged to have with us a panel of distinguished scholars renowned for their experience in climate variability, climate modeling, climate change, particularly in the areas of monsoon variability modeling and prediction. So now I invite panelists. So Professor Ravi Nanjundaya, Professor, Center for Atmosphere and Ocean Science, Indian Institute of Science, Bangalore, and former director of IITM. Sir, yes.
Yeah.
Yeah. Professor Swedan Behra, Director of Application Laboratory in Jamstack, Japan. Professor Behra. Professor Ashok Karmuri, Professor, Center for Earth, Ocean and Atmospheric Science, University of Hyderabad. And Annalisa Chechi, Senior Scientist, National Research Council, Institute of Atmospheric Science and Climate, Italy. And we have Yu Kosaka, Dr. Yu Kosaka, Associate Professor, Research Center for Advanced Science and Technology, University of Tokyo. And Dr. C. Gnanashilam, Senior Scientist, Program Director, Climate Variability and Prediction Group, IATM. And Dr. Roxy Matthew, Senior Scientist, IATM. And we have Subodh Saha, Dr. Subodh Saha, Senior Scientist, IATM. So we will begin with a round of opening comments from each panelist. To start with, I would like to invite each panelist to share their valuable insights or views about 5 to 6 minutes. On the workshop themes, monsoon teleconnections, internal dynamics of monsoon, land surface process and monsoon, lesson learned from modeling monsoon, and monsoon variability and prediction. So we would like to start the discussion with Professor Ravi Nanjundaya. You are muted. Can you unmute, sir?
Can you hear me now?
Yeah.
Yeah. Thanks. Thanks for giving this opportunity. And as far as talking about monsoon variability and the question that you have asked, I don't know what to say in 5 minutes. The only thing I can say is what I would like to mention, maybe others didn't really, maybe for lack of time, is the recent kind of the slew of models that are coming out from with AI, where they are making a massive leap. Every week you look at any new model coming in, and you think that, okay, this problem was we were not able to solve with AI. Now they're able to solve it. Like previously it was said that data assimilation was a problem with them. They could never do it, but now they have come to an end, almost an end-to-end kind of a thing where everything could be done with AI. One of the major problems that I still see, I mean, whatever I have read about, maybe I may be wrong, is, on the seasonal scale, you can get very good predictions. Sometimes even the seasonal scale prediction, let's say the Indian monsoon, I just kind of confine myself to that. You will see that you can do it well in advance, and maybe even 1 year in advance. I have seen with our own models that we could get reasonably good scales up to about, let's say, a correlation of about 0.6 to 0.7 a year in advance. But when it comes to the intra-seasonal scales, there has been one of the best papers that I've seen is by Bach et al. But still, I find that the skill is still very modest. You do get very good skill in the short scale range, and you get it on the seasonal scale. But in between, it's almost like a graveyard of predictability or prediction is in the intra-seasonal scales, which is where it is very important for us to look at the active break cycles and also the ISO cycles and everything. And maybe when we look at its prediction and its variability, I think that's where we may have to kind of concentrate on that particular point. The rest of it, I mean, I think I'll leave it to others to discuss.
Thanks a lot, Professor Ravi. And I would like to invite now Dr. Behra for his views.
Thank you, Dr. Josti, for this opportunity and everybody. Yes, I cannot agree more than Professor Nanjundaya. So we are doing well now with AI machine learning, and the predictability is better on the long lead time because these statistical models depend on signals. and the signals are getting better as you go on a longer lead times. I think Osaka-san mentioned about the 1 year delay in the predictability. So somewhere we have better signal 1 year ahead, which AI machine learning models are capturing well. And the problem, as he said clearly, that the issue is on shorter time scale, especially on intraseasonal scales and on regional scales, not for the whole India, but for certain regions. And there we started finding new signals, and some of them coming from the land vegetation, land hydrology, and also the urbanizations and other things. Besides, of course, the physics. I think Cherchison mentioned about the dynamics, the role of dynamics, but on shorter scale, probably thermodynamics also is playing a role, especially for the kind of rainfall we are seeing. Intense rainfall and not so intense rainfall, but prolonged rainfall. When you kind of divide the rainfall into several categories, short term, long term, intense, not so intense. The monsoon used to be like a continuous active phase for at least 1 or 2 weeks. But nowadays it is changing, and it is changing for not only for the teleconnections, but also for the physics and the hydrology and land vegetation. So those need to be focused more to improve the regional predictability, which has a better applicability than the ISMR. The All Indian Summer Monsoon Rainfall is an index, and that index is for economy. That index is for politicians. But for actual use, we need to have them on regional scale. And then we have a lot more players coming into play, and not only ENSO, IOD, and other oceanic variabilities or large-scale variabilities coming from like breaks, blocks, atmospheric blockage in Europe or the Atlantic, whatever. We are having more complexity in that, and then the picture gets even more complex, and we need to address them. And thankfully, we have the AI machine learning now, so hopefully we'll be able to get more linkages and processes linked to our predictability. I'll stop there. Thank you.
Thanks a lot. Yeah, you brought out very important point. Regional rainfall predictions, like particularly India, as we have seen recent years, it is changing. Now I would like to invite Dr. Annalisa for your views.
Yes, thank you. So I perfectly agree also with Vera-san that mentioning the importance of the processes and the importance of hydrology and vegetation and land interaction with the atmosphere. I think that from a modeling improvement perspective, these are fields where there is need of more work to be done. As for the use of machine learning and artificial intelligence, I think that we can have gain now thinking of how many data we can have and can use to train and to have information to guess on the future. But at some point, if we don't have the correct representation of the physics and the dynamics, we will arrive at a point where we cannot go and improve anymore, because if we stop to have, unless we have a lot of data that from one side can help more in the short scale, should help more in the short scale than in the long scale. So that is something that probably could have also could be considered at the same time. And another thing that I want to mention, and that was related to something that Surya presented this morning, and that could help in improving the representation and eventually even the prediction of the scale, is also associated with the representation of the diurnal cycle and how we can have realistic diurnal cycles that can help either the weather time scale but also the climate time scale. So I think that this aspect could be an opportunity to have the two communities somehow working together to develop more and to have more insight in this, up to the limit of the resolution, of course, but could be an interesting way of improvement. And for now, I say this, and then we'll see how the discussion goes. Thank you.
Thanks a lot. AI and the physical model seems to, I think we will have a lot of discussion on that. And then I would like to invite Dr. Kosaka for your views, insights.
Thank you very much. I'm also interested in the AI machine learning prediction. And I talked about the dynamical model prediction and seasonal extended prediction, and to see what brings the seasonal predictability of the monsoon. And but still, the prediction is subject to the model bias, of course. And AI or machine learning may be able to avoid such model bias and potentially provides even higher predictability. And that's one opportunity. But on the other hand, I still believe process understanding is important. This is kind of philosophy or ethical issue. So the forecast affects human lives. So we should not just depend on statistics or AI, but we still need to be confident about giving a prediction or forecast, and then we still need to evaluate what provides the prediction and how can we explain the origin of the prediction. And then in that case, we still need a dynamical understanding is important to convince people on the prediction. That's one thing that comes to my mind. Another thing, the second thing is interseasonal, shorter time scale prediction and more regional representation of prediction. And I'm currently interested in land-atmosphere interactions. And but even for like ERA 5 reanalysis, the soil moisture data is still subject to uncertainty. So the observational record may be essential, as well as the process understanding. And that kind of data and the process understanding will improve the prediction of shorter time scale and regional interseasonal variability. And last thing just come to my mind while listening to Annalisa's talk was that here I live in Tokyo, and it's East Asian summer monsoon season. But in the western part of Japan, the rainy season has apparently ended last month, which is record earliest event. And a few years ago, in the eastern part of Japan, including Tokyo, also saw a record earliest and termination of the rainy season. And actually, analysis talk introduced, and also in our former projection, was that the rainy season will extend under the global warming. But actually, these recent several years, we saw record short rainy season here in Japan, and so I'm thinking I'm starting to consider something is wrong in the model representation. So I still think maybe extratropical dynamics or monsoon tropical dynamics. I'm not sure, but I still need to think about what's going on. So this is just my personal note. So thank you very much. I stop here.
About Kosaka, and yes, process understanding on the shorter time scale is definitely important, particularly in mid-latitudes where you are talking about Japan. So mid-latitude dynamics are definitely need to be understood more. So I would like to ask Dr. Ashok Karmuri for your views and comments.
Thank you, Justin. Just this morning, I was just checking the news and I find this, the rainfall in pre-monsoon season has increased decadally over North India, and it seems to be decreasing in the last 2 months. So many things are happening, these small changes in the monsoon, and is it global warming or what is it? And how does it, how is it relevant for our prediction? So these are some of the questions that pop up. You may or may not have an answer right away, but decadal process, slow changes, all these things have a role, starting from smallest scale, your MTC to your monsoon depressions to low pressures, and how the models are able to capture them. Seasonal prediction, definitely the skill comes from seasonal processes, but cumulative rainfall is coming from day-to-day rainfall. So the bias correction has to focus on even the small scale processes, small scale mechanisms. We have to all see that, whether we can capture them with the model or through some sort of theoretical basis, whether we can do some sort of, for example, mid-latitude, we can capture them and theoretically, right? You can predict it maybe 10 days back, 15 days before, and can it be translated into a predictive skill? This is, there are multiple facets that we have to look at improving the skills. In the morning, we're also talking about microphysics. I think Surya was mentioning about it, and I think the slide showed some sort of amplification, some parameterization, but we have data. We have KIPEX data, we have LIDARs, we have radars. Can we use them to improve our microphysics if it's so important? Probably with that can be done. And then another factor we didn't discuss much. Of course, we talked about land surface process. We all talked about urbanization and anything. Dust. We know dust is increasingly, it's not only natural dust, but human emissions, whatever you call aerosols. They must play a big role in weather prediction, and we know they're playing a role in climate change. And why not we consider that in seasonal prediction and extended range? Maybe this is something we should worth checking in places where it's dominant. I think these are some quick points that come to my mind. Yeah, thank you.
Thank you very much. So bringing out some important points. So capturing these mesoscale plus synoptic scale process in the model, and also importance of dust in the seasonal prediction. And now I would like to invite Dr. C. Gnanashilan for his views.
Thank you, Justin. I will agree with most of the speakers that the process understanding is the key for the monsoon prediction at all time scales. And I agree with most of you that the land surface processes and the land surface feedback could be one of the less tested field which we should explore now, because our initial experiments showed that if you have improved the land surface interaction in the model, it can improve. The models can show much improved the teleconnections, even the ENSO teleconnections and the IoT teleconnections. So I think this may be one of the key aspects, but less explored, we should work on. And we mostly look at the teleconnections in based on one climate mode, but the interaction between different climate modes and how they impact monsoon is also less explored. I think we should see whether what is going on, what is wrong in the models in getting those the interaction between different climate modes. For example, many models get some of the climate modes right, but the interactions are not represented well in these models, but they would be primarily responsible for the even getting the seasonal rainfall and the regional distribution. And I do agree with Bhairasan that the regional rainfall prediction is the key, because the predicting the seasonal rainfall over the country doesn't give, the expected the output. So we need to do that. But can we take the help of both dynamical model and AI in getting these? Because the dynamical models are have now improved in getting the seasonal rainfall right, but the regional distribution is very bad. But can we take the help of AI in that? So this is another area where we should focus on our application of AI. Yeah, so, and we should also look at the different modes, because if you look at the teleconnections in the recent years, many of the teleconnections have showed very weaker the correlation with Indian summer monsoon rainfall. For example, the one anticipated the climate mode IOD, which is showing very weak correlation with ISMR in the recent years, whereas in the 90s, so they played a very key role. So what is that missing understanding? So that is to be understood, explored, because and the Indian Ocean and the Pacific interaction. So did we really understand very well? And the models have always showed difficulty in getting the ENSO teleconnection to Indian Ocean. The same what we see in the Indian monsoon. Models normally overestimate the ENSO response. Similarly, you can see the over response on the Indian Ocean as well. So probably that is suppressing some of the local processes which is evolving in the Indian Ocean. So maybe I'll keep the other points for later discussion. Thank you.
Thanks a lot. So thanks for bringing out some of those valid points like land surface feedback and ENSO Indian Ocean teleconnections and changes in teleconnections with time and multi-teleconnections seems to be important. How the models are capturing these teleconnections definitely have impact on monsoon. Now I would like to invite Dr. Roxy Matthew for his views. Roxy.
Yeah, thanks, Justy. Great discussion today through wonderful presentations and good discussion now as well. I have 3 points to make. One is about the IAML. The broader, I will say, the broader scientific community has reached a point where the IAML is constrained by physics. So physics-informed AI models are here already. So we should take that up. So these are IAML models which not only has gone through the data, but also are constrained by the laws of physics, laws of conservation of mass, momentum, energy, and all. And at the same time, there is a scope for us to constrain that with the equations of motion or fluid dynamics that we know. So that's a possibility that I see, and I'm sure in the next couple of years, that is where the Earth system science and the community is going forward with. And I'm saying that the monsoon community also should take that momentum as soon as possible. Now, the second point that I want to make is in regional variability, as I showed in my presentation also, and many others also mentioned here. Many times we end up focusing on the all India monsoon rainfall as one entity, which is a misrepresentation of that spatial variability. And this is important when we look at teleconnections, simulations, forecast skills, everything. So that is quite important. And for that, we need both observations and modeling focused at that scales as well. And there comes my third point, which is on the less understood, less known, drivers of variability, which Sheelan was just talking about. Others also talked about. Land surface processes are quite important. There itself, vegetation plays an important role. Land surface changes play an important role. All this sometimes, depending on some year to towards the interannual variability, it contributes up to 10% sometimes. So it can be a crucial factor to our monsoon forecast, and we haven't kind of reaped that drivers of predictability and all, and that needs not only observations and modeling and that scales, but also people, hydrologists, people doing land surface modeling, and all coming together with the met modeling teams to incorporate and integrate this into the models. So those are my three key comments. I think the monsoon community should take up beyond the general modes of variability and all, which we understand to a large extent. Thank you.
Thanks, Roxy. So you made a point like AI models, and we need to consider regional patterns of rainfall, and then hydrological model linking to the AGCMs would be useful. And now I would like to invite Dr. Subodh Saha for his views. Subodh.
Thank you, Jesse. I would like to point out that if you see the Indian summer monsoon forecast history from 1900 or so, we have only, unfortunately, seen only in all India rainfall. And till now, if you see the model also, we have good scale of 0.7, let's say, in all India. But if you go to a grid point, it's horrible. So we need to understand why. This why we don't have grid point regional scale, but we get the all India rainfall quite good, I would say. So this is a very important question we need to understand, and probably it lies in on the rainfall distribution pattern, that what makes the seasonal rainfall. There is we have discussed today. There are all those depressions, and then how they come, what is their track, what is their rainfall distribution. If you see that rainfall by single synoptic system, single low pressure system, they change the course of the seasonal rainfall, and their distribution is very random. We don't understand which year, what way those depression will go and where they will rain more. Okay, so probably a model cannot capture certainly. Probably AI model can help us in this direction, that how this distribution will be there. And not only the synoptic system, but if you see the rainfall from MESOs also, their contribution is very different from what we see in observation. So, for example, MESO is contributing, let's say, 30%, okay, but model is giving you 70%. So that makes a lot of mismatch, and then there is this kind of problem. If we can focus, probably we'll get the improved skill in a regional scale. There's a one point I would like to mention. And then another point is that we have talked a lot about predictability from ocean, but there are other players also coming in, like Tibetan plateau, we have forgotten almost. So there are many papers that come in that it may affect through land surface temperature. And if you see the model, our model is doing very bad. It cannot retain the memory of land temperature. Within 7 days it goes. But if you observation, you see there is a memory of month or so. So those things are missing in model. And then how they affect some phases of monsoon, not the whole monsoon, but some initial phase of monsoon. And they have some contribution on, of course, in subseasonal scale forecast. The last point I would like to mention that everybody is mentioning land surface and all those things. So it's very challenging area, because if you see in a country like India, the landscape is changing every year. You have very rapid change in irrigation, for example. You have very rapid change in urbanization, So how do you cope with this, all those things? These are all kind of data, organization, irrigation or data year by year, as well as the processes. We understand some of the process, but most of the things we don't understand. So those things are missing in all these forecast models. If you see the weather forecast model, definitely they will play a very big role in short term. But in our weather forecast model, none of the model they can include urbanization or irrigation, those kind of effects. So this is the area I think we need to focus to improve this monsoon system. Thank you.
Thanks, Subodh. So you brought out some of those points that are talking about like urbanization and LULC. Also, Tibetan Plateau seems to be these days Tibetan Plateau amplification is important. If models are not capturing that, there's going to be a problem. Yeah. With this, I would like to
Jasti?
Yeah.
Ashok here. Just I would like to add just sort of one point here. We are talking of teleconnections, regionalization. The teleconnections to local areas and different timescales also may be different, and regionally too they will be different, right? We are not focusing on these things because we think that it has no value. Probably it's the time we have now. The time has come to make a. I didn't have time to talk about this in the morning. We have to make a concerted effort with a dedicated time. Identify the local drivers to have the predictability and take a short climate period. Don't take 50 years because things are changing. So your target in the 20 years, still that will be your PDO signal, everything will be there. So you take this, you focus on this and locally start with subdivisions, the teleconnections changing are, which are the drivers that are most important, and then start developing, your regional models, AA plus AML plus, try to go at a high resolution or regional models. Anything can be done. It should be community effort. It cannot just be sort of with one model we do that. This will be difficult. So then I think this is something we have to put effort. It's a lot of donkey work, but that has to be done. This is just sort of a personal opinion, but I think people can discuss and comment about this thing. Thank you.
Thanks a lot, Professor Ashok. Definitely, yes, these teleconnections are changing from region to region within like Indian subcontinent. If you see, North Indian region has different teleconnections compared to South Indian, and then these days rainfall is also increasing, and so impact also increasing over the Northwest India. So yes, if you, as you suggested, if we can actually develop AI-based models plus physics, and then that will be definitely useful. So the opening remarks on this are wonderful. So with this, I would like to thank all the panelists for bringing out fundamental issues to improve understanding on monsoon variability and prediction. So now we have specific questions to panelists and invite them to trigger more discussion on a specific question to a specific panelist. So I would like to again start with Professor Ravi. So now predicting spatial distribution of ISM rainfall is an important task, as the panelists already expressed their usefulness of this regional rainfall. How well are the dynamical models predict the spatial pattern of ISM rainfall at least a season in advance? So, and what needs to be improved in the models to predict these regional patterns? So, Professor Ravi.
Jasti, you have put a very tough question. I don't know where to start from that. Okay, I don't have the numbers to say how well the dynamical models are doing for seasonal forecast and whether they're getting the patterns right. Pardon me if I'm wrong, but I do feel that, okay, quite often they get it wrong. One of the measures, let's say if you look at the Indian monsoon season, almost all seasonal forecast models have a dry bias. So if you start with the bias itself, obviously the spatial pattern is going to be very different. You can look at anomalies, but not everything can be kind of explained in terms of anomalies. Given that we are looking at a very nonlinear system, the actual numbers may have a different meaning. Yeah, 2-degree anomaly, or let's say of SST, is very different from let's say a 1-degree anomaly when we are looking at the base is either 20 degrees centigrade or 29 degrees centigrade. So there's a huge difference. So I mean, coming back to the point, we do have one of the things that we need to look at is the dry bias, and the spatial distribution will again be wrong, because quite often if I remember correctly, but the peak of the rainfall is always a little south of what you see in the observations. So that's another problem. So obviously, I think there is a problem with the spatial distribution. Now, how do we get it wrong? I mean, how do we get it right is a tough problem. But one of them could be, or whatever I have read about, is that the SSTs themselves, there is a large error in their prediction. So that could be one of the reasons. The teleconnections, as we have seen, or as Surya pointed out and others also pointed out, dynamical models have too far a strong response to teleconnections. Some of the teleconnections may not be correct. For example, if I remember correctly, IoT Indian monsoon teleconnection is a little weak. It has been a little weak in the recent past. But it's the response, the way that it should respond at times is also wrong in some of the dynamical models. These could be some of the things, and of course, the way we put in other aspects, let's say land surface processes, how boundary layer processes, there could be large errors in that, which could be kind of creating, a poor structure of, even if you're looking at the seasonal mean rainfall. Just at the top, these are some of the things that we can kind of discuss about and could improve for them. Thank you.
Thanks a lot. So the dry bias seems to be, looks like is dominant in these coupled models. And of course, SST bias in Pacific as well as the Andes tropics seems to be important. Yeah, thanks for bringing out the interesting point. Now, following that, I would like to invite Behra Sain for. So, is the ENSO going to be a main player in altering the intraannual ISM variability in the future? If not, what could be the other major climate modes we should take into account in order to predict the monsoon?
Okay, thank you. And I'm not sure if ENSO will be the major driver in the future, because as you have seen in my presentation before, the ENSO monsoon relationship has gone to higher level and then gone back to almost zero. And as you see in the recent decades, the ENSO monsoon relationship has strengthened, no doubt about that. But then if you believe in the past, we believe in next 1 decade or so, the relationship will come back to again to the weakest points. Having said that, we have the global warming now, and that is a black box. For me, it's at least the black box. We don't know how that is going to influence both the tropical ocean variabilities, tropical ocean atmosphere coupled variabilities, and in turn, how they are also going to influence the interbasin relationship and the teleconnections. So in that sense, global warming is posing a kind of unknown factor in our projections to understand how ENSO monsoon, how IOD monsoon will evolve in the future. If you remember Analysason's presentation, so she showed the IODs are going to be more intense and more frequent in the future. And if that happens, and the IOD monsoon teleconnection gets strengthened in some of the decades, we'll see a completely different picture than what we are seeing now. Having said that, we all talked about the model biases, and the biases coming mostly, as I understand, the models are doing well to capture the SST variabilities in the tropical ocean at least, because these SST variabilities are mostly determined by the ocean dynamics. And ocean dynamics are well captured by the ocean models now. So in that sense, we are doing very well to capture NINO3 index, the IOD index, and other indexes from the coupled models. But the problem is in the rainfall. And most of the models are not capturing the rainfall in the right place and the right time. And that's where the teleconnection is coming from. So unless we resolve that, and also we know how they are going to evolve in the future, I think it will be very difficult for us to clearly project how these tropical climate variabilities are going to change in the future and how their influence is going to change in the future. I'll stop there. Thank you.
Thanks a lot, Hussein. Yes, there are a lot of studies talking about the extreme and El Ninos or multi-land air seem to be increasing the global warming. So we don't know how they're going to really impact the monsoon. So with that, I will put another question to Dr. Ashok. Are the models good enough to predict the ENSO diversity? If yes, how to improve ENSO teleconnections to Indian summer monsoon? If no, how to improve prediction of ENSO diversity itself?
Are you asking who?
You are Ashok Kaguli.
Okay. Well, I'm afraid of late I have not been working on the topic, but Behra-san probably can answer that better. But definitely, there is challenges if you see Venju Chai's work and all, how they. It's again there is a lot of spread among the models, but whether it's canonical El Nino or Modoki El Nino, first question is whether whether El Ninos occur or La Niñas occur more. You know, this is another embedded question. It's very, very challenging. Definitely models are not doing so well in capturing the distinctions till 3 to 4 months before the event. In 2010, there was this nice paper by Harry, Hendon and Wang. They show that, up to in the first few months, the models cannot say whether it's El Nino or El Nino Modoki, but after that, in the beginning, just as the event comes, they are able to capture. This is as far as the seasonal prediction is concerned. You might also want to recall Nandini, Ramesh, and Raghu Muttagudde, who talk of ENSO prediction in the subsurface 2 years back. The funny thing is, the distinctions between El Nino and El Nino Modoki in the SST, they are so clear, but La Nina and La Nina Modoki distinctions are not so clear, but in the subsurface, both of them are different. So this is as far as we're talking about El Nino. And then we talk of the basin-wide warming events that are coming now, 2009, 2014, and more recently, I think there was one more year which looked like a basin-wide, but it didn't happen. So many types of El Ninos are coming and their impacts globally. Indian monsoon, fortunately, everything affects more or less. If you take average, it's the same. But definitely we need a lot of improvement in this aspect, El Ninos, type of El Ninos and their intensity.
So do you think that subsurface dynamics plays important role for in order to predict these ENSO diversity or flavors?
Yes. I think a lot of work has been done by Shamal in IITM. So the type of the signal, lead signal before what type of El Nino that you want to see and where it's shoveling, you can see them almost 2 years before in canonical case. And Modoki case is not so early because the signal is a little weak, but you can see them in different types. And also with Sahai, we did some work. Again, Shamal's thesis, from what stage to where you can go. This is sort of his SOM method. So this sort of a AML method, if I'm correct. So use these simple techniques, simple yet proven techniques, proven studies to use and see whether that makes sense and whether that has any predictability to monsoon at different stages. Shamal is very much in IITM. So somebody can check this as a small paper and see how this works. Definitely there is predictability.
Yeah, we agree with that. You can definitely see signals associated with El Nino 2 years in advance, but what kind of El Nino is going to be? It's very difficult to say that it can be.
No, that's what I'm trying to say. While in the surface, the signal may not be there. In subsurface, it's there. The question is whether the signals that we see, be it in Shamal's papers or be it in Raghu's papers, the signal, whether it's strong enough to be used as a predictor or is it a tenuous signal, statistically significant, but may not really be harnessed. This someone has to look at in a prediction point of view. Definitely it's there. The distinctions when you do the composite, that's significantly different in subsurface. Whether that signal is sufficient to predict El Nino, a type of El Nino, and then if so, that needs to be examined. I think that's
exactly. A good topic. So how these subsurface signals are communicating to surface and how it is modulating SST is a question. So now
there is also a lot of people have been working on Bjerknes feedback at different, we do it in concurrent time scale, but you can also take the lead lag of this thing. This is it. All this simply you take the basic ways to start with correlations, whether this works or not, as simple as that. If it works, fine, in terms of predictability.
I have a question to Dr. Ashok.
Yeah.
See, when you have information in the subsurface, for a canonical El Nino, that's fine. That signals can come in the upwell in the East Pacific.
Yeah.
But now, when a Modoki is happening, how the subsurface information comes to the surface in the Central Pacific?
Well, that's a question. How deep is the mixed layer if you put an Argo buoy? Yeah, I think it can capture it. That's what I'm trying to say. Is the signal strong enough in terms of statistics? Otherwise, if you sound Eastern Pacific or you sound Central Pacific, the thermocline, how deep is it? I think you should be able to capture the signal.
Book says that thermodynamics are more important for capturing this Modoki type of rather than subsurface. Maybe we need to look into it.
Yeah, see, this is what these are the questions we have not totally understood. For that matter, ENSO monsoon, I don't think it's a solved question, or complete El Ninos we did not debug. If you see our Modoki paper, Yamagata sensei put a very nice statement. Just like biology, all species, we should examine each case. We talk of El Nino, canonical El Nino, then we found this basin-wide warming, big cases in 2009 and 2012, 14. So some of it is because of global warming. Even Modoki is a sort of modulation by decadal variability. And there was this lot of question that these events are statistical sampling if you remove the two cases. No, they're not. We showed that even without those cases, these are weaker El Ninos with a different characteristic. They're there. The distinction is there. Only thing, people have to work on that. Now, I don't think anyone, at least in India, we're not working, maybe Behra-san or somebody in Japan or somewhere else.
No, even for the subsurface surface interactions, I think the interbasin relationship becomes very important. How the MJOs propagate to the Western Pacific,
right.
How the IODs evolve in the Indian Ocean, and how that wind, because wind becomes an important factor for the tropical Pacific. When you connect subsurface with surface, winds play a big role, and that could be also linked to the other basin, not necessarily always coming from the same basin.
Thanks a lot for a nice discussion. And adding to this ENSO complexity, we know frequently the IOD occurs, co-occurred with this El Nino. So Indian Ocean is rapidly warming, and the characteristics of IOD is also changing in the future climate. So how does it modulate the monsoon? So this question belongs to Anais Jesse. May I ask your response?
Yes. Okay. Yes. So the information that we are having is how the Indian Ocean dipole is changing in the future, and the effect that we are expecting on the monsoon is associated with also what Behra-san was saying before. So we need to think that there is a changing in the pattern of the precipitation as we have seen it up to now, if the IOD becomes the main driver of the teleconnection. It is important also to mention that in any case, we also need to think of how this is represented in the different models and what is the variability that we have in these changes. So either in terms of what is the changes that we are expecting for the IOD, but also for what are the processes that are represented in the models in response to this, because all the diversity and all the discussion and the different type of mechanism and so that have been recorded in the past literature are also associated on how the models represent this teleconnection. So we know that there are differences, but we know also that there are different models that can represent differently this. So then we have to find a way to rely on what is the more realistic representation of that, and then think of how this change in the future, and then how we can trust this change and what can be the consequences of this.
And there are studies. There are studies suggesting that the like IOD also has some kind of flavors. So what do you think? These flavors are really valid and that they are going to work for the monsoon predictability?
So you said the answer and IOD.
Different types of IODs. Are they going to be useful for the monsoon prediction?
Yes, it could be. And one important point is that in the models, the IOD is not, has very peculiar characteristics. So now we know that the eastern pole is represented differently with what is effectively occurring in reality. So there is an overestimation, an overrepresentation of some features of the Indian Ocean dipole. So that is something that may affect our understanding, and eventually and of course, may affect the projection, but mostly may affect our understanding of what is what is happening and what may happen in the future.
Yeah, thanks a lot. It seems that if we have multi modes in action like IOD and so I think that's always a competition. Which one is more dominant? So with this, I will move on to next question to Dr. Kosaka. Interaction between mid-latitudes and tropical circulation plays an important role in modulating Indian summer monsoon variability. However, climate model shows limited skills in capturing these interactions. Any suggestion on how to improve interaction between the mid-latitudes and tropical circulation in the models, and then its impact on the predictability?
Yeah, something like from ENSO. I'm sorry, coming back to ENSO, but the part of ENSO is driven by extratropical dynamics, like or subtropical dynamics, like a Pacific meridional mode drives ENSO. And we have shown this in the extratropical pacemaker simulations. So one thing is that I don't know if this is underrepresented or not, but this is definitely an extratropical process that can affect Indian or Asian summer monsoon. And another thing is that the recent study not very recent, but some studies in Japan had shown that the waveguide teleconnection in the summer season across the Asian jet, we call Silk Road teleconnection. It can drive tropical convection by inducing low-speed wave breaking over the Western North Pacific. And then this low-speed wave breaking produces cold upper level cold low or cutoff low, which eventually evolves sometimes into tropical cyclone. And then the tropical cyclone activity drives teleconnection like the PJ pattern and something. So this kind of representation, this kind of extratropical to tropical influence requires at least a high resolution, because it's wave breaking is a nonlinear process. So this kind of process representation, I don't know how this is correctly represented in the prediction models. And nonlinear process, and including lossy wave breaking, maybe provide additional prediction or improvement in the model representation of the Asian monsoon.
Thank you, Professor. So the point is that if the models cannot capture this Raspberry breaking or cutoff loss, and they may not be able to communicate the large-scale circulation changes to the tropics. And then when you said that if the extratropical circulation is influencing tropical circulation through PJ pattern in particular, so that is going to have a certain impact on the monsoon. So that the link of these teleconnections may be from mid-latitudes to Western Pacific, and then it is to Indian Ocean. So it's a very interesting point that we are also working in the same line. So now we'll go to next question, that is to Dr. C. Gnanashilan. So frequency of decadal climate modes are changing, say PDO, IPO, for example, from low frequency to recent years quite high frequency. So how would they influence the monsoon variability and predictability? And also, what could be the possible ways to improve the decadal prediction of Indian summer monsoon rainfall?
Yeah, I do agree with you that the frequency of the PDOs are increasing. It's mainly because when the surface warms, the ocean becomes more stratified and the Rossby waves travel faster. So making that higher frequency in the PDO cycle. But how does it affect the monsoon? That's a big problem, because if you look at the ENSO-monsoon relationship, which is largely influenced by the presence of PDO. So it's not the ENSO-monsoon relationship, it is the ENSO-PDO combinedly affecting the monsoon. So definitely the frequency change in the PDO will have impact on the ENSO. I don't call the PDO impact, the ENSO-PDO impact on the monsoon. And again, when you talk about ENSO, there is a decadal ENSO. So that is less explored, and how the decadal ENSO connections to the ISMR, that also need to be examined in detail. And about your second question, see, all the climate models represent the PDO reasonably well. And AMO really good. But coming to the decadal prediction, most of the models predict the AMO very well, whereas they fail to predict PDO in advance. So one of the possible reasons could be the PDO initiation is forced by AMO, but AMO PDO, the initiation lag time is about more than 10 years. So the information from the AMO, which is the main trigger for PDO, is not sufficient to incorporate in a decadal prediction model. That is one of the bottleneck you can call in predicting the summer monsoon decade. Whereas, so this is again the teleconnections from the PDO, but we need to explore the other. One more challenge is that the statistics shows that the Indian Ocean cooling is favorable for good monsoon. But you know, the Indian Ocean has already warmed up to a level where all these theories may be wrong. So how the current, the teleconnections with the different climate modes, I think we need to understand it better, because they all may be undergoing a lot of changes, which we have already witnessed in changes in many of the climate modes. So that could be a really challenging problem, maybe. And this is what you can answer. And one more before I close it. So I also request that request to all the panelists that at the end of the panel discussion, if we can come out with some recommendations on some efforts, the multi-modal sort of efforts, especially on the topics which is highly debated, and most of the members have unanimously are convinced, was the importance of land surface representation in climate models in making the regional precipitation better. So I think if we can recommend some multi-modal effort to ICTM, maybe we can get support. We can do it for a good cause. Yeah, maybe at the end of the panel discussion, we can discuss on this more.
PDO, the recent is what we observed as well, like PDO and the associated with ENSO seems to be increasing, and that have strong impact on the monsoon. So, and then we have a next question to
can I just seek a clarification from Ganashilan about Silan, you're mentioning about intensive, what's that, frequency changes in PDO? What does it mean?
The PDO cycle. So from the 20 to 30 years cycle to the 10 to 20 years under the global warming.
Is it not a sampling issue? Don't you think it's a sampling issue? Can we say that with conviction?
Yeah, they experiment, because people have done experiments with the models where the frequency change is very, very clear, and which can be seen even in the past records, that the frequency change is very clear. But in a farming scenario, it's most likely, because when the stratification is more, the waves can travel faster, because it's not the equatorial basin. It is in the mid-latitude basin. The Crosby waves takes years to travel. But any little acceleration on that will increase the frequency of the PDO. It's very likely one.
Yeah, one thing that's also, because you're talking of decadal things, decadal Indian Ocean dipole has a good decadal prediction, at least in two models, as we have seen. But there is no long-term skill for Pacific ENSO beyond 1 year or 1.5 years. Where is this skill? The skill for the IOD seems to be coming from Southern Ocean, whether you take it in ORAS or SODA, or these couple of models, Mirok and one more model, I don't remember, but only 2 to 3 models. And even in CMIP 6, there are only 2 to 3 models. Is it some sort of what is happening? Why is it not coming in Pacific? Is there no connection with Southern Ocean, or is our study fundamentally result is very tenuous? Why are we getting a better skill in decadal time scales for Indian Ocean dipole, not monsoon? And the signal comes in.
Yeah, one thing
not Pacific ENSO. Yeah,
I understood that. So one thing we do not have much understanding is the impact of Southern Ocean. So we need to have more understanding of how the Southern Ocean or the higher latitudes influencing the tropics, especially on the impact of Southern Ocean on the tropics, need to be understood very, very, very well.
So, partly to answer Ashok sir's question, is that ENSO, for example, is highly driven by like internal dynamics, and then Indian Ocean is with external forcing is more important than the internal dynamics as per the literature. And so when you have a strong external forcing, obviously you're going to have a better skill over the Indian Ocean. Maybe not for IOD, at least for basin-wide warming. So with this, we'll move on to next question. So tropical SSTs is known to impact the Indian monsoon rainfall. Under the global warming, how the tropical SSTs are going to change, and its influence on the Indian summer monsoon. Also, the current observational network is good enough to understand the monsoon process or improve the prediction, and how to improve the historical record of rainfall over India. Is there any possibility? So, Dr. Roxy, can you please take up this question?
Great. Thanks for that question, important question. Definitely tropical SSTs are increasing. And if we look at the future projections, the SSTs are, the current SST increase and the changes are quite dwarfed by the future changes. So far we got to see something around 1.2 degrees Celsius per century in the Indian Ocean. And that is going to be somewhere between 2 to 4 degrees Celsius per century, for the coming decades, if you are going to take the SSP5 scenario, the high emission scenario. So it's quite large change that we are going to see in respect of oceanic changes, especially in the Indian Ocean, which is a landlocked ocean and which has strong connections with not only monsoon but also cyclones and other weather systems. Now the thing with the future projections of the monsoon in relation to the SST is that it's a very tricky thing, and there are two factors. One is many models are able to represent the thermodynamic impact of increasing SST. So increasing SSTs, there is more evaporation moisture, there is more rainfall, more or less connecting with the Cauchy-Clapeyron relationship. And in a region with high moisture convergence, instead of 7%, you would even see up to 10% increase in rainfall per degree Celsius. And that is happening. That is the current set of CMIP models are picking up this thermodynamic response in a great way, wonderful way. But at the same time, the dynamic response of these models are totally wrong many times. So you would see that even in the historical simulations, whatever changes in the monsoon that we are seeing, whether it's decadal variability or long-term changes in the monsoon circulation, the monsoon winds and the rainfall are not captured by the CMIP set of models, especially if you consider the ensemble mean. And that is because the gradients are represented wrongly because of multiple processes that we discussed about. They are not represented or simulated well in these kind of models. So, for example, the SST gradients itself, or the temperature gradients, or the tropospheric temperature gradients in the CMIP models are sometimes even opposite to what we observed in relation to the historical simulations. So this results in the wrong dynamics, and we would see many times the thermodynamics is overpowering in the models. So if you take an ensemble mean of these models, all the CMIP models, including CMIP 6 and CMIP 5, we would see that the future monsoon is definitely increasing even in the nearby decades. But one of our in-depth study which is ongoing shows that if you select the models based on both the thermodynamic representation and also the dynamic representation, and see how the monsoon is evolving in the future, we would see that the monsoon circulation and the winds and the rainfall are declining a bit until around 2050. And then it is after that the thermodynamic response. There is more moisture than the dynamic weakening to compensate for the weakening. And after that, it's the thermodynamic response that is dominant post 2050s. So if this shows that when we are thinking about climate change, we need to be careful about how the models are representing the dynamics along with the thermodynamic factors. So that's a key factor I want to key message I wanted to give. And observations, they are still not adequate enough, especially if you are talking about subsurface dynamics and all, like what Ashok and Shilan was talking about. If you want to capture that subsurface dynamics for prediction or long-term understanding long-term changes, we need much more high-dense observations, not only in the Indian Ocean, in the Pacific as well, and in the Atlantic also. All this. So recently we did a stock taking of all the tropical ocean. So it is called Pan-Tropical Observation Review. It's online in Frontiers, and you can see it discusses about why we need to go beyond one ocean basin and think about trans-basin interactions. And also, when we are thinking about observational platforms, we need to think about this all tropical oceans as one entity, because if you don't measure in Pacific and Atlantic, it will affect here as well. So this has to be a community. The climate community have to work together to make sure that the observations are well taken or well in place. Yeah.
Thanks, Roxy. So the thermodynamics and dynamics seems to be like important. And another point is that atmosphere is going to be stabilized as you see in many studies brought out. So how it is impacting these ocean atmospheric interactions in the global warming? That may be also very important aspect. How the monsoon might be changing.
Yeah. So I'm sure this is also a key factor. And I'm sure when we talk about thermodynamics and dynamics, the stability of the atmospheric profile also is important. But I do not have key insights on that aspect to provide anything valuable at the moment.
Okay. Thanks a lot. So now we'll move on to another question, Dr. Subodh Sahab. So what kind of impact does LULC has on the monsoon variability and predictability? How good are the current models in representing the land atmosphere interactions, and how to improve these interactions in the model?
Well, this is basically some study basically shows that they affect locally, mainly locally. Locally, for example, they can change the distribution pattern. Some studies shows that to have a right kind of land use land cover, so they change your moderate event mainly. Okay. And if you talk in our forecast system, they actually we don't know how they will react to actual land use land cover, because those things are not very good. Even this land use land cover is not very updated in your forecast system, and urbanization, irrigation, it is totally is not there. So those effects are not very clear.
Okay, so new I think models are being developed for LULC. I don't know if they are implementing, so how they're going to actually are going to increase the skill in those new generation models.
That we have to see. Most of the studies are done in regional model like WRM, but not in this.
Okay, thanks a lot.
Can I just make a comment on that, Subodh?
Please. Yes.
Yeah. See, LULC doesn't, except when it rains and you talk on weather scale. Definitely, even on weather scale. Hello.
Yeah, please go on.
I think I got cut. So If you use latest data sets like your NRSC data, for as far as initialization is concerned, this is a quite decent data, which we did for some extreme event cases simulations. But the question, as I see, when you want to give a prediction, Subodh's question comes as how you predicted. I mean, when you predict what would happen, that's a good question. But at least on a weather scale, probably using NRSC data and then sort of keeping it persistent for 3-4 days. I don't know whether it makes sense. Just it's a good point to check. I think with the observations that are available till the model is developed, can we use that? I mean, this is something people can think about.
Okay, so yes, the means quality observational data sets.
Or you tune the model with this?
Yeah.
This data sets that you are having at half minute, I guess, the data. So,
yeah. So we were talking about land assimilation. So is it going to be useful? So
It will definitely help, but also there are some processes which are not very good in model. For example, if you see the vegetation, how it is done. So you don't have very good description of evapotranspiration, for example, and then you see the root zone, soil moisture, how it takes moisture from root zone. Let's say, for example, break time. Break time you don't have, it's quite dry, so a lot of moisture comes from subsurface. So those representations are not really good in model. It's very crude way it's done. So those are things also there apart from land use, land cover processes.
But you brutally force with NRC data, that's the vegetation, let's say, for a season. Okay, whether it's break or based on that vegetation, it will do the evapotranspiration, right? Does it help?
Not really, because if you have, for example, it will take moisture from subsurface, right? And if this process is not well repented, so then you will miss those parts.
Sure, subsurface is the
In addition to this, actually, currently the new models, they have the subsurface flow also represented well, and there is an interaction between the subsurface to surface, which is also represented. So I think we need to move forward and adopt those type of models to have very realistic representation of vegetation or land surface processes. I think we need to really go ahead.
Again, I would like to thank all the panelists for their detailed answers for the questions that are posed to you. And now we are ready to take some of these questions from participants. Please, I think Soumi seems to be waiting for a long time. Are you there, Soumi?
Yes, sir. Means it was more of some comment I like to made that time about when Ashok sir was making point about El Nino and Modoki. So we have a paper with Silan sir also in that paper, revisiting research discharge processes, and we showed there that the Central Pacific El Nino, if we consider only the subsurface processes, has no predictability. So in the subsurface, and there are a few also different work with my postdoc where we showed that the it called trade wind charging, and that is actually when the North Pacific oscillation has two type of role. In one is through heat flux, that is called North Pacific meridional mode, and that can be one predictor of the Central Pacific El Nino. So when we choose simple El Nino indices, sometimes it actually mislead us because Nino 3 is not is like you don't know it is a East Pacific or it is a Central Pacific El Nino. So and many different type of index is actually force artificial signal. So we have to be very careful about when we are talking about these indices are only taking the Central Pacific or only taking the East Pacific. So our paper in GRL showed that the way we collect the CP and CT El Nino is very important, and based on that you can see the teleconnection impact on all over India or world. So that's but a really nice presentation and nice workshop, sir. Thank you so much.
Thank you, Somi. Good to hear from you after a long time. Let me clarify what I was saying. First, I was not talking about surface index, okay? And even surface index, the reason for defining El Nino Modoki as 3 boxes, and there is one more rider there, persistence for more than 3 seasons. It's not CP. That's a distinction, okay? El Nino signal always goes through Central Pacific. Trans Nino, Trenberth has defined it since long time back. So that is different. We are talking, that's why there is a different index, and there are a lot of nonlinear indices. A lot of work has been done about surface, subsurface, not you, not Shamal, and many people have done that. Definitely the thermocline change is there. Just see whether that change is it significant enough to give a prediction. Of course, the signal comes from Northern Pacific. The basin-wide warming is associated with seasonal footprinting. The signal comes from Northern Pacific. Kosaka-san was also talking about some sort of thing. Any signal, doesn't matter. Is it giving you predictability? Can you predict it better with a, because science is not you, not me. Is it useful to predict? If it is, you are able to predict with lead, go ahead, see that and see how important, whether you can harness that to predict something else. As simple as that. Anything subsurface, I still believe there is some predictability. People can check that. Okay, take the cases in the models and compare it with observations. What is the fluctuation? And if it works, fine. If not, that's fine. It's a question of whether it's practically useful or not. That's all.
Yeah, thank you, sir. And I really want to ask Subodh sir about the land use land cover change. Like so, if you means like if I see some recent data with field capacity, it seems that like the Punjab area has a lot of change in the land, like their agriculture and that kind of. They have like less soil moisture capacity. Do you think this kind of change can actually reflected on the models, climate models, or is it not necessary for climate model to have these kind of changes? Just to get an insight.
Oh, very good question. So it depends on scale actually. For example, what we were using, let's say climate model CFS, it's 100 kilometer or so. In this scale, probably it won't be very different. But if we go for weather scale, let's say 6 kilometer, 10 kilometer model, then it will be definitely there will be some effect. But often we don't have those kind of very high resolution data, surface data. And generally model, practically what we do, generally we take the course data and interpolate. So there is a lot of compromise in this area, but I think it is a very important area that we should focus, and it has a potential to improve weather scale at least.
Okay, thank you so much, sir.
NRSC provides data, high resolution data for small regions. But we need high resolution data for a pan-India region, right? Pan-India level data.
It's all over India. It's available, Seelan. You can download it from Bhuvan.
Yeah, but that's a coarse one. She's talking about fine resolution. You are talking about
meter scale, or I think it's less than meter scale, right? I don't know, Subodh, that can comment, but definitely I think the data is available.
Some data people have created. But if you go to subsurface, this is the same data.
Subsurface, no.
Only a surface data.
Surface,
and that is also some kind of created with a very coarse sample.
Right.
I just want to add that in India, there's an effort to collect all the soil moisture data available with all the agencies and grid them over pan-India level. And that product may be made available very soon. So maybe within a year. So we will have a soil moisture graded product. So that will definitely improve the understanding of the land surface feedback. So hopefully it will be an important step.
Thanks, Sophie. Thanks, Sophie. And do we have any question from participants?
Sir.
Start. Need.
Sir, can we add these factors like industrializations also while considering a new method? Industrialization plus your groundwater agriculture as one of the factors while calculating the regional predictions.
Yeah, so you are talking about very micro scale details, but we have not, our modeling, we have not reached up to that level. But regarding the groundwater, so currently the development has been implemented and it is there. So those, the groundwater information can reach to the surface. So that interaction is, more realistic represented in advanced models. Yeah, but it is a long way to address all these. But urbanization and all, yeah, there are models, but they're not running. Some of the climate models they take into account of the urbanization. It's clear.
Industrialization also.
Industrialization, I don't think so.
It comes in urbanization category.
Yeah. Any other members want to answer that question? Yeah, Soumi, yeah, please answer.
Yeah, so it's not about modeling though, but means I want to just highlight that we did some work with the Pune urbanization, and the result of rural and urban cities really quite remarkable, and like it is like few kilometer you can see tremendous change in temperature pattern, diurnal temperature variability, and so I think in a long run when more and more urbanization happened, it can impact a lot, but currently to go that label in climate model or maybe very difficult, but yeah, regional model maybe we can think about, and many other places it is happening. But like 2-3 degree temperature change in happening in the urban and rural areas in Pune, that data is showing, and I was quite shocked to see this kind of changes, and mainly nighttime the changes is happening. So also that maybe the land cover has a very strong impact, because the moisture is also another important issue which is reflecting on the rural and urban changes. So just for a remark, like, because one student did some work which is very good work, I felt. Yeah, thank you.
Thanks a lot, Swami. So yeah, Ashok. Yeah.
I think Behrasan is waiting before me.
Okay.
After that, I'll talk.
Okay, so in this context, I want to bring another factor in. I think we discussed about it earlier this morning. The role of aerosols and dusts. I think if you increase the temperature, you increase the capacity to hold moisture. But converting moisture into rainfall, you need those nuclei. So that will come from aerosols and dust. So I don't know how the urbanization or the other factors are going to contribute to the more aerosol in the atmosphere so that we get more rainfall. That's one factor. The second factor is like as many of you are discussing, we see some changes in the rainfall in Rajasthan and Punjab. That's mainly because we have more irrigation now. Some of the regional models are able to capture them. I'm not sure if the global models will be able to capture them in one issue. The other issue is once we make those areas green, they are going to lose the dusts. So what will happen next? You have more greenery. Will that lead to more rainfall or less rainfall? That's another factor we need to think about.
Thanks, sir. Ashok.
Yeah, adding to Soumi and Behrasan, we did about for South India. Of course, we're talking of rainfall point. Hyderabad, Chennai, and Kerala per se. So we did about 15 extreme cases with WRF with this NRC data at high resolution, 1 kilometer. I don't know whether you call it as high resolution anymore. WRF, several cases. Definitely, urbanization, greenery. Change of greenery, urbanization has increased the extremity by changing the fluxes. This is one thing. But this result, as we discussed, is subject to your soil moisture, because once there is rain, how the evapotranspiration, etc., happens in the rural areas is a question. Urban areas, it may not be a big problem. And again, as Behrasan mentioned, dust. We did it recently for Saudi Arabia. Ramakrishna was working in IITM. He published a nice paper, dust impact on climate, diurnal cycle. It's again, there is a lot of non-linearity. How much dust you have, signal seems to change. To add to the complication, if you come to India, it's not dust alone. So many things are there. There are a couple of papers on Delhi aerosols and all. The results are not exactly, what you call as in agreement with one another. I think this is an open question. This is something one can record and see the role of dust in weather prediction. This is what I was also mentioning. And diurnal cycle, definitely temperature is nighttime temperatures in places like Delhi or anywhere. So aerosols play a major role. And soil moisture, these two factors, this can be sort of flagged as important aspects. Irrigation is another animal, but that's much more difficult given the data, lack of data thereof.
Yeah, thanks, Ashok sir. All micro scale process must be included in those regional models. Now we have one more waiting for this question, like Aditi Deshpande. Aditi, are you there?
Yeah, I'm there. Thank you so much for this entire day of talks and discussions. Just as a thought that floated into my mind while the panel discussion was going on is, do we have an understanding or ongoing work on how compound events are feeding back into monsoon variability as well as extreme events? Because I know that there was a discussion Roxy mentioned about how there is a sort of a tug of war between thermodynamic and dynamic constraints over monsoon, and that of course has some level of impact on how extreme events happen. But in addition to that, I think what I've seen to be glaring obvious is the Indo-Gangetic Plain region, where there's a lot of drying happening, like the rainfall is reducing as well as there are heat waves, and that seems to be creating a compound effect. So how does that, or multiple compound effects which we may or may not be able to identify or be aware of, how are they feeding back to changes in variability either on a regional level or even on an all India seasonal scale? So if any of the panelists have any thoughts on that, or what kind of, if there is any work being done, I'd love to hear that. Thank you so much.
Yeah, Aditi has brought out a very important point, and I don't know anybody has really.
Maybe if I
even identify.
Yeah.
If I come in, on that. I think that's an interesting scientific problem to take up. Maybe some of the young early career researchers here can take this as a problem. And I'm sure, for example, the pre-monsoon conditions. If you take the example of 2024 monsoon, we had reduced rainfall along with heat wave just before the monsoon. And along with that, that's cascaded. I mean, along with that, we had, I think, cyclonic conditions as well. I don't remember 2023 we had a similar situation, or I'm mixing up between 2023 and 24. But regardless, we have kind of cascading and compounding, climate events in the pre-monsoon state, which could feed to the monsoon onset and the progression and all. So I'm sure this is something, and this is at different time scales. Sometimes we see, long rainfall deficits and the Indo-Pak region heating up along with the heat wave. At the same time, there are, sometimes cyclones in the Arabian Sea or Bay of Bengal kind of diverting the monsoon as well. So different time scales. But this can be considered as a compound event working on different time scales, different regions, but affecting the monsoon. So such kind of insight will be definitely good on how the monsoon onset happens, how it progresses, and all. Interesting scientific problem. Somebody can take that up, I guess.
Roxy, before that, the question is, there are compound events, there are compound events. They look like all, are they just stochastic combination of random, or can you get enough sample to study? It's the first, what are the compound events that we can define? Multiple compound events, as Aditi puts, not just compound. And we have sample, or it's a
some of them might have, I mean, regionally, static events like, for example, the dry conditions along with a heat wave might be repeating multiple times with enough summer conditions. The cyclone, I said, okay, that's the additional kind of something that happens, could be random here and there, but there are other conditions which we might be able to, take up.
Yeah, I totally agree. The compound events could be related to each other. And we did some analysis and modeling using AI machine learning. And then one factor came out very strongly, that's the soil moisture again. So if you don't have a good soil moisture observations, I think you are going to fail in the modeling and predictions.
Yeah.
Also, I'm sorry I didn't raise my hand, but if I may ask, so this is something that has, as I'm not someone who's an expert in soil moisture and land use and land change dynamics, but the fact that soil is not a monolith, we have a different form of or a large scale coverage of soil variability also, which probably has a different kind of feedback depending on what soil we are looking at. Like, how do we account for that kind of parameterization in models, if at all we do, and can there be a way forward? A question to anyone who may want to answer.
At the moment, we are just using the reanalysis data, whatever is available to us. So we have not seen yet the sensitivity of different soils, and also the soil moisture from different layers. We have not seen that yet because we don't have enough observations and we don't have enough reanalysis data on that. And when you are going for a global scale kind of modeling, we need a reanalysis data gridded everywhere. So that's a real big problem now for us.
Okay. Thank you so much, everyone.
Do you hear me? Sorry. Yes, I just wanted to add about this, that at CNR we are doing some analysis and improvement in the land representation in models. And actually, we started to do some experiment where we have improvement in the representation of the variability of vegetation, for example, or the variability or the changes in the albedo. And there are indications of improvement in the scale, but we didn't do any analysis on the monsoon yet. So it could be that this kind of experiment could be also interesting also for the kind of aspect that we are discussing now. But yes, we don't have a look at them yet, but there are options that could be improvement there. The problem in the models is that has been said, so we lack observation use for the validation. We lack information on observation for the understanding of the processes. And in most of the models, there are most of the processes are not there. So there is still a lot of work to be done in global models for this aspect. But there are room for having something.
Thanks a lot.
Sorry.
Go.
Yeah, thanks for the great panel discussion here. So my question is about the complex intraseasonal timescales and their forecasting in the available global models. So with some understanding, we know that once the monsoon circulation, the background monsoon circulation gets established by July and into August, we do have a better understanding of how the intra-seasonal waves can propagate with the well-established background, like for example, in easterly shear, and how that can be enabling northward propagations. And saying so also on the interannual timescales, when we have a well-established background forcing like ENSO or IOD, we do still have a good source of predictability on how these intra-seasonal waves will behave. Since the background, either the climatology or the interannual signals are well established. But speaking of these subseasonal oscillations during the onset phase, and it seems from observations or from available model forecasts, it's quite challenging to get these forecasts on extended range, especially during the onset phase. Even within a particular model, say example for the EFS or the ECMWF, the ensemble members are quite diverse, even with a lead time of more than 5 days. Within the signal is lost within the first 5 days. So that onset phase being a very significant, very important phase for the agro community. And we don't have a good amount of a good source of predictability in that phase. Especially that becomes more challenging when the background interannual signal is either not an ENSO or not an IOD. It's just a normal kind of a neutral, but still the source of predictability is really bad. So do we have any thoughts on this in terms of model development, or do we? I don't think so. We have a theory also to explain these this phase, onset phase, subseasonal variability. So any thoughts on this? Thanks.
So you are talking again the very high noise to signal ratio. So if you have high noise, your predictability will be always low. So there is no doubt about that. And the ENSO IOD brings the signal. So if you have some years when you have ENSO IOD, the chances of getting signal to noise ratio is higher. Signal will be higher. So that's why I think predictability will be higher. In the non-IOD, non-ENSO, and non-climate mode years, I think we need to work a lot, especially for the local vegetation and local land impact on the monsoon.
Thank you. Thanks a lot, Rasim. So do you have any other question from audience? Yeah, please.
Hello. Yeah, this is Bhupendra. This is not a question, but a comment to several of the points which the panelists have raised, and recently partially Dr. Aditi also raised regarding the availability of soil moisture data and whether the different kind of soil and its porosity or the composition can have different kind of feedbacks. So the first thing is, as far as the climate and weather community goes, is to first get reliable estimates of soil moisture, irrespective of whether what is the soil type, what is the soil composition, and along with that, getting the right evapotranspiration fluxes. So once we get these two things right, then at least even within the subseasonal scale, we can get the land processes and land atmosphere interactions correct in some ways. Right now, we are trying to get and construct a pan-India soil moisture grid data, And we have actually proposed, Pan India project for that, collaborating with ISRO and many other institutions to not only get the data on the surface, but we are also getting the high resolution satellite estimates through NICER project. So all those things are going on, and we hope to get some good the soil moisture data in the years to come. Thank you.
Thanks a lot, Bhupendra. So your new data set probably is going to very useful for the seasonal prediction. And if there is no more question, so I will. It has been a quite enlightening discussion, and I would like to thank each and every panelist here for their time and the explanation they have provided and the suggestions to the youngsters. So it is quite useful discussion. Thanks a lot. So I will now hand over the floor to Dr. Ghanshi. Thank you.
Thank you, Chaudhary, for conducting the panel discussion very nicely. And I thank all the panelists for insightful discussions and throwing many ideas and open questions. So it's good if we can come out with some recommendations. Maybe I will circulate the minutes to the all the panel members, and we take feedback, and then if we can post it as some recommendations to ICTM. Maybe something will happen. So let us all hope for that. And I thank all the panelists, especially Bhaira-san, Osaka-san, and Annalisa Churchy-san. So because they, and of course the other panelists also. But I also thank Jati for conducting it nicely, and Vineet and Rose has conducted the morning sessions very well. And overall, it's wonderful discussions we had. Of course, we all learned a lot of things, and definitely these discussions are thought-provoking, and definitely a lot of young scientists and students are here. So I'm sure they will get benefited from these discussions. And I thank all the participants and speakers and the Director IATM and all the people who helped us in making this happen. And I also thank IAMAS, ICTM, and Dr. Tara, and who has been pressurizing all the members. So I am pressurized to conduct this workshop, but at the end, we learned a lot. So thank you all. So hope we will be able to bring out the recommendations and it will get implemented. Thank you all.
Thank you.
Thank you. Thank you. It was a pleasure. Thank you.
Bye.
Vineet has some announcements.
Yeah, with this, we bring the workshop to a formal close. We also take this opportunity to express our sincere gratitude to everyone who supported the smooth coordination of this event.
I think bye from my side. Bye, guys. I think the meeting is over, right?
Thank you all.
Yeah, we express our gratitude to everyone who supported the smooth coordination of this event, both directly and behind the scenes. Your collective efforts have played a vital role in making this workshop a meaningful and successful experience. Thank you once again, and we look forward to continued collaboration and future interactions. We warmly invite all participants and dignitaries to join for tea now.
Please send some.
We don't get it.
Send some, even gifts to us. Me and